Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. You are here now, settling in, breathing slowly, letting the day fade into the background, and allowing the quiet of the night to open into something wider, something deeper, something as vast as the universe itself. Tonight, we drift gently toward one of the oldest questions the human mind has ever held. What came before the beginning of time? The words themselves carry a kind of stillness, a hush, like standing at the edge of an ocean, so wide that it seems to merge with the sky. And yet, this is not simply a poetic question. It is a scientific one, a question that reaches directly into the foundations of cosmology, physics, and the way we think about existence. But for now, you do not need to solve anything. You do not need to grasp every detail. Your only task is to listen softly, to let the ideas drift through your awareness like slow-moving clouds. And if you begin to feel sleepy, that is perfectly fine. This is a space for curiosity, and also a space for rest. When we ask what came before time, we are already standing near the limit of ordinary language. In everyday life, time feels obvious. There is a past, there is a present, there is a future. Events follow one after another, like beads on a thread. A clock ticks, moments pass, we grow older. So it seems natural to imagine time as a kind of endless line, stretching backward without limit and forward without end. And on that line, we picture the beginning of the universe as just another point, somewhere very far back, perhaps at the start of everything. And then, just behind that point, we imagine there must be something else, another stretch of time, something that came before. Because in our everyday experience, there is always a before and always an after. But when physicists study the universe, they discover something astonishing. Time, as we experience it, is not an independent stage upon which events unfold. Instead, time is woven together with space itself. The two are not separate. They form a single fabric, a structure sometimes called space-time. This idea comes from a theory called general relativity, developed to describe gravity, motion, and the geometry of the universe. In that framework, time does not simply flow, like a river existing on its own. Time is part of the shape of the cosmos, and the shape of the cosmos is shaped in turn by matter, energy, and gravity. So when we talk about the beginning of the universe, we are not just asking when matter appeared, we are asking something even deeper. We are asking when time itself came into being. Modern cosmology suggests that our observable universe was once much hotter, much denser, and much smaller than it is now. From that state, space itself began to expand, carrying galaxies with it, stretching distances over billions of years. This gradual expansion is what scientists refer to, in simple terms, as the Big Bang model. It is not an explosion in empty space. It is space itself growing, evolving, changing from a high-density state to a cooler, more diffuse, and more structured universe. From this perspective, the phrase "the beginning of time" means something very specific. It means that if you trace the history of cosmic expansion backward, letting the universe grow smaller and smaller in your imagination, you eventually reach a limit, a point beyond which our current theories can no longer describe reality. And at that boundary, time, as defined within our expanding universe, simply does not extend further. This is not a wall, not a barrier, not even a physical edge. It is a conceptual limit, a place where our mathematical descriptions lose reliability. And the question, what came before this moment, may not have the same meaning it does in everyday life. So tonight we enter this territory slowly, calmly, without rushing to conclusions, because the truth is, science is not certain about what, if anything, preceded the birth of our universe. Some theories suggest possibilities, others propose entirely new ways of thinking about time, and some gently suggest that the word before may not apply at all, but rather than feeling frustrated by uncertainty, we can learn to appreciate it, to see it as a sign of honesty and humility, a reminder that the universe is larger and stranger than our language alone can hold. Imagine yourself now, floating in a quiet darkness, not a cold darkness, but a calm one, a darkness filled with distant starlight, each star a tiny signal from across space, whispering its history, billions of years of fusion, light, and cosmic evolution, all of that light traveling outward until finally it reaches you, here, now, in this quiet moment, and behind those stars, larger structures, galaxies, clusters, filaments of matter stretching across the cosmic web, all of it expanding, all of it moving through time, and somewhere far in the past. This entire story began, or at least, that is how we currently understand it. Yet even this understanding, grounded in observation, data, and careful theory, carries mystery, because when we ask, what is time, really, we discover that physicists, philosophers, and thinkers of every age still wrestle with the question, is time something that exists independently, flowing whether or not anything changes, or is time simply the measure of change itself? A way of describing how one configuration of the universe becomes another. Is time fundamental, or is it something that emerges, like the surface of a lake arising from the collective behavior of countless molecules? In our daily lives, we rarely need to ask such questions. We wake, we live, we sleep, clocks tick, calendars turn, but at the deepest level of physics, time becomes subtle, delicate, almost elusive. And when we push these ideas to the earliest moments of the universe, language begins to tremble, concepts begin to blur, and yet, even here, there is still something profoundly calming about staring into the unknown, because the unknown is honest, and honesty is peaceful. So as you listen, allow yourself to release any pressure to fully understand. These ideas are enormous, and the brain, like the universe itself, sometimes works best when relaxed. Let the words drift by. Let them become part of the quiet. If you find yourself drifting into sleep, that is perfectly natural. You are not missing anything. You are simply moving gently along the same current of time that everything in the universe shares. Human beings have always wondered about beginnings. Ancient cultures created stories to explain how the world began. The sky, the earth, the stars, each story reflected the beliefs, hopes, and mysteries of the people who told it. Today, science offers a different kind of story, not a myth, but a description built from observation, from instruments, from mathematics, from slow, careful reasoning. And yet, even the scientific story contains vast stretches of mystery, unknowns that stand like mountain ranges in the fog, visible in outline, but not yet fully mapped. This is especially true near the beginning of the universe, where temperatures, densities, and energies reach extremes far beyond anything we can recreate directly. Where our theories are pushed to their outer limits, and where time itself seems to soften, blur, and perhaps transform. Still, we have learned much. We know that the universe is expanding. We know that distant galaxies are moving away. We know that the cosmos glows with a faint background of ancient light, a soft radiation that fills space in every direction, like the residual warmth of a once blazing furnace. And we know that the elements within our bodies, carbon, oxygen, nitrogen, all were forged in the hearts of stars, then scattered into space, before eventually becoming part of planets, part of oceans, part of us. So when we think about the beginning, we are really thinking about the origin of everything that allows us to exist: matter, energy, space, and time. And yet, here's where the question deepens, because if time itself began with the universe, then asking what came before may be like asking what lies north of the North Pole. A beautifully shaped question, but one that does not quite fit the geometry of reality. It is not that the answer is hidden, it is that the answer may not exist in the form the question expects. This is difficult, but also strangely peaceful. It frees us from the need to force the universe into the shapes of our ordinary intuition, and invites us to listen instead, to observe, to imagine, to accept that reality may be stranger, more subtle, and more beautiful than we can fully picture. So as this exploration unfolds, we will remain grounded, calm, and clear. We will not chase speculation for its own sake. We will not reach for dramatic conclusions. Instead, we will walk slowly, step by step, through what is known, through what is uncertain, and through what may lie just beyond our current understanding. And all the while you are free, free to reflect, free to rest, free to drift. Because curiosity does not need tension, it can exist side by side with tranquility, like a quiet lantern in the dark. The universe, in all its immensity, has given rise to living beings capable of wondering about it. That alone is extraordinary. Somewhere within billions of galaxies, on a small planet orbiting an ordinary star, a mind like yours can lie in the dark, breathing slowly, thinking gently about time, about beginnings, about existence itself. And whether you stay awake or slowly dissolve into sleep, the cosmos continues, expanding, evolving, unfolding its story, moment by moment, or perhaps all at once, held in a deeper structure we are only beginning to glimpse. So let this be a welcome, a soft invitation to curiosity without strain, to science without hurry, to wonder without fear, and to the possibility that simply asking the question, what came before the beginning of time, is itself a beautiful expression of what it means to be human. Rest here, in the space between knowledge and mystery, in the quiet, in the stillness, where thought becomes gentle and the universe feels close enough to whisper. Imagine you could gently rewind the universe, not in a sudden jump, but slowly, like watching a long, smooth recording in reverse. Galaxies drawing closer together, clusters of galaxies contracting, the great filaments of the cosmic web thickening and tightening, stars rearranging, moving inward, gas clouds compressing, temperatures rising. As you continue to rewind, everything becomes denser, hotter, more uniform. The structures that once defined the large-scale universe begin to blur, until eventually there are no galaxies, no stars, no planets, only a nearly smooth, glowing fluid filling space. This is not fantasy. This is the picture that emerges. When we take the laws of physics that work today and apply them backward in time, step by step, carefully, this picture is what scientists mean by the Big Bang model. Despite the name, it is important to be precise. The phrase Big Bang can be misleading. It suggests an explosion, something detonating at a particular place, hurling matter outward into empty space. But that is not what the model describes. In the scientific picture, there is no central point from which matter flies outward. Instead, space itself expands. The distance between distant galaxies increases over time, not because they are racing through pre-existing emptiness, but because the underlying geometry is changing. The fabric we spoke about earlier, the fabric of space-time, is stretching. When that fabric is rewound, distances shrink, densities increase, temperatures rise. When it is run forward again, distances grow, matter dilutes, temperatures fall. This is the true sense, in which the universe has a hot, dense past and a cooler, more diffuse present. To keep track of this evolution, cosmologists use a concept called cosmic time. Cosmic time is not the personal time on your wristwatch. It is not the time measured by any single observer. Instead, it is a way of labeling slices of the universe's history. Imagine a series of snapshots. Each snapshot shows the large-scale universe, across many billions of light years, at a particular stage of its expansion. In one snapshot, the universe is smaller, hotter, filled with ionized gas. In another snapshot, it has expanded, cooled, formed neutral atoms. In later snapshots, the first stars appear, then galaxies, then larger structures. Cosmic time is the parameter that orders these snapshots. It is the time measured by an idealized observer, moving with the overall expansion, not drifting rapidly relative to the average motion of galaxies. This observer sees the universe change in a simple way, from hot and dense to cool and structured. Cosmic time is defined inside the model, inside the expanding space-time. It does not refer to some external clock, ticking outside the universe. Now, when physicists say time began at the Big Bang, they are speaking about this cosmic time. They are saying that when you trace the history of expansion backward, the model reaches a limit, a smallest value of cosmic time. You cannot simply subtract another second or another fraction of a second and expect the same equations to keep working. As you move toward that limit, densities become so high, curvatures so extreme, that the theory of gravity we use, general relativity, can no longer be trusted alone. Quantum effects, normally small, become important, and we would need a new, unified description, a theory of quantum gravity, to continue further, until such a theory is known. The phrase "the beginning of time" marks the edge of where our current model applies. It does not mean we have proven that nothing existed before. It means our definition of time, as given by this expanding geometry, cannot be meaningfully pushed beyond that point. Without new physics, why do scientists trust this picture at all? Why not imagine any arbitrary story? The answer lies in observation. The Big Bang model, in its refined modern form, is not just an idea, it is a framework that explains many independent facts. First, there is the observed expansion itself. In the early 20th century, astronomers measured the light from galaxies. They noticed that the spectral lines, the fingerprints of elements, were shifted toward longer wavelengths, a redder part of the spectrum. The farther away a galaxy is, the stronger this shift. This is interpreted as evidence that distant galaxies are receding from us, not because we are at the center, but because space itself expands, carrying galaxies along, like dots on the surface of a balloon. As the balloon inflates, the distance between the dots grows. This observation of a correlation between distance and recessional speed is one pillar, supporting the idea of a dynamic, expanding universe. Second, the universe is filled with a faint background of microwaves, radiation in the form of very low-energy photons, coming from every direction, almost perfectly uniform, but with tiny irregularities. This background is understood as the cooled remnant of a time when the universe was dense and hot, a time when matter and radiation were tightly coupled, when the cosmos behaved like a glowing plasma. As the universe expanded, it cooled. Eventually, atoms formed and light decoupled from matter began to travel freely. That light has stretched, its wavelength lengthened by the expansion of space. Until today, it appears as a nearly uniform, cold glow. The temperature of this glow, measured with great precision, matches what the hot Big Bang model predicts. Its small variations also match the patterns expected. If tiny fluctuations in the early universe grew under gravity to form galaxies and clusters, this background is like a baby picture, a snapshot of the universe, when it was only a few 100,000 years old, and it strongly supports the general outline of the model. Third, the relative amounts of the lightest elements provide further evidence. Hydrogen, helium, and small quantities of lithium and other light nuclei exist in ratios that align with calculations of nuclear reactions in an early, hot, dense phase in that period. Protons and neutrons, the building blocks of nuclei, interacted frequently, forming light elements. The predicted mix depends on the density and temperature of that early phase. When those parameters are chosen to match observations, the model reproduces the observed abundances with impressive accuracy. This process, called primordial nucleosynthesis, is another pillar supporting the Big Bang framework. Three very different observations, cosmic expansion, background radiation, and light element abundances, all point to the same broad story, a universe that was once hotter, denser, and more uniform, that has expanded and cooled over billions of years. Still, even with this success, there is a region, very close to the would-be beginning, where the picture becomes uncertain. If we follow the equations of general relativity all the way back, we find that certain quantities, such as density and curvature, seem to blow up, to become infinite. The scale factor, a measure of the size of the universe, appears to go to zero at a finite value of cosmic time. This is sometimes described as a singularity, but the word singularity can be misunderstood. It does not necessarily refer to a real physical point, where everything is compressed to nothing. It often signals that the mathematical framework we are using has broken down. When infinities appear, it is usually an indication that essential physics has been left out. In this context, it suggests that we cannot trust classical general relativity. At extremely high densities, we need a theory in which the gravitational field is treated quantum mechanically, just as matter and radiation are. Only then can we say with any confidence what actually happens at those earliest times. The realm in which these quantum gravitational effects become crucial is sometimes associated with the Planck epoch. This is not an exact moment, but a way of indicating a scale of time and energy at which our familiar theories cease to be reliable. The Planck time is an extremely tiny interval, so small that if you tried to express it, you would need a 1 followed by about 43 zeros in the denominator. It represents a rough limit beyond which our current combination of quantum theory and relativity cannot simply be extrapolated. Similarly, the Planck length is an unimaginably small distance. Again, a 1 divided by a 1 followed by about 35 zeros in meters. These scales are not magic boundaries, but they mark the territory where space, time, and energy may lose their familiar meaning, where the notion of a smooth space-time may give way to something more granular or more abstract, depending on the yet-to-be-completed theory of quantum gravity. In that regime, the question of before may need to be phrased in completely new terms. This brings us back to common misconceptions. One of the most persistent is the idea that the universe expanded into an already existing emptiness, a pre-existing space, waiting to be filled. But in the standard cosmological model, space itself is what expands. If you imagine the early universe, you should not picture a small sphere of matter exploding into darkness. You should picture all of space everywhere in a very hot, dense state. Then, over time, the distances between points increase. No outside region is required. No external void. The question, what is the universe expanding into, may be like asking, what is the surface of the Earth expanding into? If the Earth were to slowly swell, from the point of view of creatures living on the surface, distances along the surface would grow, but there would be no need for a larger, higher dimensional space for them to imagine, in order to describe that expansion. Similarly, the universe's expansion does not require an outer container. The geometry itself is all that is needed within the model. Another misconception is that we know the universe began from nothing. In a strict sense, physics does not conclude this. The model describes how the universe evolves from a very hot, dense condition. It does not yet tell us why that state exists, or whether it emerged from something else, or from some kind of different phase, or from an entity, where time is not defined in the usual way. When people say, before the Big Bang there was nothing, they may be speaking loosely. From the viewpoint of the equations, we can only say that cosmic time, as defined in the standard model, has a smallest value, and that our description does not extend beyond it. The question of what, if anything, preceded that remains open and is very sensitive to how we define time. This is why the word before must be handled carefully in our daily lives. Before is tied to a simple, one-dimensional timeline: breakfast before lunch, childhood before adulthood, today before tomorrow. But in cosmology, time is intertwined with geometry and reaches a boundary where the concept itself may need to be reworked. If time is a property of the universe, if it is part of the fabric, then asking what came before is like asking what lies outside the fabric, what reality looks like, without any reference to earlier or later. That may be a meaningful question. But it cannot be answered by simply extending the familiar line of time further to the left. It may require a new language, a new set of concepts, perhaps a theory, in which time is not fundamental but emerges from something more basic, or a theory in which time behaves differently, near the earliest stages, becoming more space-like or dissolving into something we do not yet fully understand until such theories are confirmed. We acknowledge, with calm honesty, that our current use of before may not apply at the deepest level, yet even this limitation is not a dead end. It is a signpost, pointing the way to deeper physics. The success of the Big Bang model in explaining what we observe gives us confidence that we are on a productive path. The breakdown near the beginning tells us exactly where our understanding needs to grow, and the careful examination of what we mean by time, space, and beginning reminds us that the universe is not obligated to match our intuition. Our task is to refine that intuition, to let it stretch gently until it can hold new shapes of reality without breaking. For now, you can let these ideas simply settle. The Big Bang model as a description of a universe that evolves from hot and dense to cool and structured. The expansion of space, not an explosion in space. Cosmic time defined within that evolution, evidence from expansion, from background radiation, from light element abundances, the incompleteness of the singularity picture, the need for quantum gravity, the role of the Planck epoch, the clarification that there is no external void, and the realization that before may require a new kind of understanding. All of this can rest quietly at the back of your mind, like distant galaxies, visible but not demanding. You do not have to hold on tightly. You can let go, let thought drift, let the universe with its beginnings and its mysteries continue to unfold while you breathe, rest, and gradually, if it comes, slip into sleep. If you imagine the universe as a vast, curved, ever-changing fabric, you are already holding the essence of one of our deepest theories, a framework called general relativity. It describes gravity, not as a force that pulls objects across empty space, but as a manifestation of the geometry of spacetime itself. Mass and energy tell spacetime how to curve, spacetime tells mass and energy how to move. Planets orbit stars. Because the spacetime around the star is curved, light bends near massive bodies, because it follows the straightest possible paths. In a geometry that is not flat, black holes form when matter collapses so tightly that the curvature becomes extreme and even light cannot escape. On the largest scales, this same framework describes an expanding universe where the average distance between galaxies changes over billions of years. It has passed every test we have been able to devise, from the orbit of Mercury, to the bending of light, to the timing of distant pulsars, to the delicate patterns in the cosmic microwave background. As far as we can tell, in the domain where gravity dominates and quantum effects are small, general relativity works remarkably well on very different scales. A second great theory describes the behavior of matter and fields at the smallest, most microscopic levels. This is quantum mechanics, extended and refined into what is often called quantum field theory. Here, particles are not tiny, solid beads. They are excitations, ripples of underlying fields. Each type of particle corresponds to a particular field. Electrons, quarks, photons, all arise as quantized disturbances of these fields. The rules of this microscopic world are not the rules of everyday experience. Outcomes are often probabilistic. Systems can exist in superpositions of states. Interactions are described by amplitudes that must be combined and then squared to obtain probabilities. Despite its strangeness, quantum theory is extraordinarily successful. It underlies the behavior of atoms, chemistry, solid-state physics, lasers, electronics, and much of modern technology. When quantum effects dominate and gravitational effects are negligible, quantum field theory is our most accurate description. So we have one theory that excels at describing the very large, the geometry of space-time, the motion of planets, the dynamics of galaxies, and the expansion of the universe, and another that excels at describing the very small, the structure of atoms, the interactions of particles, the behavior of fields. Most of the time, these domains are separate enough that we can use each theory in its own region without trouble. But there are places in nature where the very large and the very small collide, where space-time curvature is enormous and quantum effects cannot be ignored. In those places, our two great theories must both apply, and yet in their present forms, they are not fully compatible. The early universe is one such place. Densities were extremely high, temperatures were enormous, distances between relevant regions could be exceedingly small. Quantum fluctuations in the fields that filled space would have been significant. At the same time, the overall gravitational field shaped the dynamics of this young cosmos. Another such place is the interior of a black hole, or the vicinity of what classical general relativity calls a singularity. In these regimes, we cannot simply ignore gravity or ignore quantum effects. Both are crucial. And yet, when we try to simply merge the two formalisms to apply ordinary quantum field theory on a classical curved spacetime, in situations where the curvature becomes extreme, we encounter problems. Infinities appear. Predictions lose meaning. The mathematics ceases to provide clear, finite answers. This signals that our current frameworks are incomplete. They are approximations, valid only in certain ranges of scale and curvature. They are not yet a final description. To see why, consider what happens if you follow general relativity all the way back towards the earliest times. The equations that describe the expansion of the universe indicate that, at a finite value of cosmic time, certain quantities, such as density and curvature, grow without bound. The scale factor, a quantity that measures the relative size of the universe, is driven towards zero. This is sometimes called an initial singularity. But again, we must be careful. The appearance of an infinity in a physical calculation is often not a sign of a real, infinite quantity. It is usually a sign that the theory being used has been pushed outside its domain, that key physics has been omitted, and that a new description is required. In this context, The singularity is not a tiny point sitting inside a pre-existing space. It is a limit of the mathematical model where the smooth space-time picture breaks down. Quantum mechanics teaches us that on very small scales, the behavior of fields and particles is fundamentally fluctuating. There are uncertainties built into the structure of the theory. We cannot simultaneously know certain pairs of quantities with arbitrary precision. Fields that look smooth on large scales exhibit jitter and variation when examined at very tiny distances. If we try to apply such ideas to spacetime itself, we are led to suspect that at extremely small scales the notion of a smooth geometry may no longer be valid. Instead, the metric which describes distances and times might itself fluctuate. The shape of spacetime might become uncertain, subject to its own quantum behavior. If that is true, then the classical equations of general relativity, which assume a smooth manifold, cannot be expected to hold all the way down to arbitrarily small scales. We would need a theory in which spacetime and its geometry are treated quantum mechanically on the same footing as other fields. Physicists often use the Planck scale as a guide to where such effects might become important. The Planck time is defined from fundamental constants, the speed of light, which sets the relation between space and time, the gravitational constant, which sets the strength of gravitational interactions, and a constant that governs the scale of quantum effects. From these, one can combine units to obtain a characteristic time, a characteristic length, and a characteristic energy, at which the quantum nature of gravity can no longer be ignored. These Planck units are not magical thresholds, but they give a rough sense of the region where our current approximations must give way to a more complete theory, at times earlier than the Planck time, at distances shorter than the Planck length, at energies approaching the Planck energy. Our usual separation between space-time background and quantum fields living on that background may fail. Everything, geometry included, may have to be described by a unified quantum framework. The search for such a framework is often called the search for a theory of quantum gravity. Different approaches pursue different strategies. Some attempt to quantize the gravitational field in ways similar to other forces. Some propose that spacetime emerges from more fundamental degrees of freedom that do not themselves live in space and time. Some suggest that the geometry we observe is a coarse description of deeper discrete structures, like a smooth surface emerging from a lattice. When viewed from far away, whatever the details, a successful theory of quantum gravity would need to do several things. It would need to reproduce general relativity in regimes where curvature is gentle and quantum effects are small. It would need to reproduce quantum field theory in regimes where gravity can be treated as a small correction, and it would need to provide well-defined predictions in regimes where both are important at once, such as near classical singularities or during the earliest stages of cosmic evolution. In those regimes, it might tell us whether the singularities suggested by classical equations are replaced by something finite, whether the universe has a true beginning in time, or whether time emerges from some other description or behaves differently than our classical picture suggests. The early universe is in many ways the ideal laboratory for these ideas, not a laboratory we can manipulate, but one we can observe at least indirectly through relics, fossils, imprints, left on the cosmic background radiation, on the distribution of galaxies, on the statistics of structures, and perhaps on other signals, such as primordial gravitational waves. In the very early stages, quantum fluctuations in fields would have been amplified by expansion, stretching small, microscopic variations to cosmic scales. These fluctuations could seed the structures we see today, tiny differences in density, enhanced by gravity, growing over billions of years into galaxies and clusters. In this way, motions in the deep quantum regime might leave signatures we can still read. By studying those signatures, we might infer something about the physics that operated at energies and curvatures far beyond what we can recreate in any terrestrial experiment. This is why cosmology and quantum gravity are so closely linked. The universe itself serves as a record of its own earliest behavior. If we learn how to read it, we can test, or at least constrain, different proposals for what the laws of physics look like at their deepest level. In walking this line between what is known and what is conjectured, it is important to maintain clarity. There are aspects of the early universe for which we have strong observational support. The existence of a hot, dense phase, the subsequent expansion, the cooling, the formation of light elements, the presence and properties of the cosmic background radiation, the growth of structure, these are anchored in data. Then there are aspects where the evidence is indirect or model-dependent. The precise details of any rapid early expansion, the role of particular fields, the exact mechanisms by which quantum fluctuations were generated and stretched. Then there are regions where current theories are being stretched past their domain, near classical singularities, or before the Planck time. In those regions, we know enough to be cautious, but not enough to be confident. About any single story, a calm, honest approach is to mark these categories in our minds, to recognize which layers of the picture are solid, which are plausible, and which are exploratory, without cutting off curiosity, but also without overstating certainty. This is where a certain kind of scientific humility naturally appears. Not as a forced attitude, but as a simple recognition of the situation. We have partial theories that work remarkably well in their own domains but fail when combined in extreme regimes. We have clues, observational and theoretical, that suggest new directions. We have candidate frameworks that try to unify gravity and quantum mechanics, but we do not yet have decisive experimental tests to select one over the others. Rather than pretending we know more than we do, it is more accurate and more peaceful to say, here is what is established, here is what is under active investigation, here is where we are still, mostly in the dark. This attitude does not diminish the power of science. It reflects how science actually progresses by pushing into the unknown, step by step, checking each new idea against reality, keeping what works, letting go of what does not. You can picture it like exploring a coastline in the mist. Some features are sharp and well mapped, others are faint outlines. Still others are only guessed at from distant glimpses. As instruments improve, the mist thins, more shapes emerge, the map becomes clearer. But there may always be farther reaches beyond the current chart. The boundary between known and unknown is not a single cliff, it is a moving front where understanding slowly advances. The early universe and the question of time's beginning lie along that front. They are not beyond all reach, but they are not yet fully illuminated. As you rest with these ideas, you might feel that tension relax, the tension that comes from wanting a single, complete answer. Instead, you can allow the current state of knowledge to be exactly what it is, strong in some areas, tentative in others, open in many. The two great frameworks, general relativity and quantum mechanics, stand as pillars of 20th and 21st century physics. They describe much of what we observe, but where their domains overlap, in the deepest, most extreme regimes, they hint that a further step is needed, a step toward a theory in which space-time itself is part of the quantum world, a step that may clarify what, if anything, it really means to ask what happened before the beginning of time. For now, it is enough to know that the boundary where our present theories fail is not a defect to be hidden. It is a landmark, a clear signal of where future understanding must grow. The universe has told us as much in its behavior, in its radiation, in its structure. All we have to do is listen, patiently, carefully, and with a mind that is willing to balance curiosity with calm. There is a quiet but profound possibility in modern physics, the possibility that time itself is not one of the ultimate ingredients of reality, that what we call time might arise from something deeper, something that does not itself tick, flow, or change. At first, this sounds impossible. Everything you experience seems saturated with time. You wake up, you move through your day, memories accumulate behind you, plans extend ahead. The sensation of now feels as though it is sliding over a fixed, ever-growing line of past events. And yet, when physicists and philosophers look closely at the equations that describe the universe, they find that the fundamental laws have a strange property. They do not seem to care which moment is now. Many of the core equations of physics look the same, whether you run them forward or backward. If you take a movie of a planet orbiting a star, or of two particles bouncing off each other, and then reverse the frames, the underlying laws still describe the motion. Just as well, of course, in everyday life, reversed movies look wrong Broken eggs do not leap back into their shells. Smoke does not reassemble into a candle. Coffee does not separate itself back into hot and cold layers. But this difference between forward and backward does not come from the simplest microscopic laws. It comes from deeper conditions on how systems are arranged, from statistics, from entropy, from the fact that there are many more ways for matter to be disordered than to be ordered. This observation opens a door to a new way of thinking. Perhaps time as we experience it is not simply written into the basic structure of reality. Perhaps it emerges from the collective behavior of countless underlying degrees of freedom. The way temperature emerges from the motion of molecules, or the way pressure emerges from particles bouncing on the walls of a container. Thermodynamics is the branch of physics that describes how energy is exchanged, how systems approach equilibrium, how macroscopic quantities like temperature and entropy behave. In thermodynamics, entropy plays a central role, can be thought of as a measure of how many microscopic arrangements correspond to the same overall macroscopic state. A low entropy state is one where matter and energy are arranged in a very special and unlikely way. There are relatively few microscopic patterns that realize it. A high entropy state is one where many microscopic patterns look the same. At large scales, it is much more probable, because there are many more ways to be disordered than to be highly ordered. The second law of thermodynamics says that for an isolated system, entropy tends to increase over time. A hot and cold region left in contact will even out. A gas released into a box will spread. A structured configuration will tend to dissolve into a more typical, more random one. This is the origin of the familiar arrow of time. Why you remember the past, but not the future. Why things age. Why cream that has been stirred into coffee does not spontaneously separate, again, into distinct layers. Now, here's where the idea of emergent time appears. Some researchers have suggested that time might be understood as arising from the statistical behavior of more fundamental entities, much as temperature emerges from motion. In some formulations, there is a proposal, sometimes called the thermal time hypothesis. It suggests that if you have a state of a system with certain statistical properties, you can define a notion of time from that state itself. Instead of putting time in by hand, you extract it from the way the state changes with respect to particular observables. The details are mathematically technical, but the spirit is simple and striking. Instead of starting with time as a basic parameter, you start with a state and with rules for how that state is described. Then, a preferred direction of evolution can arise from the interplay between the state and the structure of the underlying algebra. In this way, time is not assumed, it is derived on a different front. Relativity offers another perspective on the nature of time. In special relativity, space and time are joined into space-time. Different observers, moving at different speeds, will disagree on the length of time between two events or the distance between them. They will even disagree on whether two separated events are simultaneous. There is no single global now that all observers share. Each path through space-time has its own version of present, past, and future. In general relativity, space-time can be curved, bent by mass and energy, but the idea that time is just one dimension, among others, persists. From this viewpoint, you can imagine the entire history of the universe as a single, four-dimensional object, a kind of block, in which every event is located, past, present, and future all coexist as parts of this grand structure. Your sense of flowing from moment to moment is then associated with tracing a path through this block, one world line among many. The block universe idea does not mean you can change the future by walking around it. It does not mean you are forced to accept some particular view of free will. It simply means that in the mathematics of relativity, all times are treated on similar footing. The laws do not single out one special, moving present. The passage of time is something experienced along a path, not something that exists independently of the structure. If we combine these insights from thermodynamics and relativity, a subtle picture emerges. The laws viewed at a fundamental level may not contain an intrinsic arrow of time. They may simply relate states without caring which way we call forward. The arrow, the directionality, emerges from boundary conditions, from the initial arrangement of the universe, from the fact that it began in a state of extraordinarily low entropy, unspeakably ordered, compared to what would be typical given the amount of energy and space available. As the universe evolves, entropy increases, structures form, then decay, stars ignite, then burn out. Information is rearranged, spread out, mixed. The direction from lower entropy to higher entropy is what we call the forward direction of time. If somehow the universe had started in a high entropy state, fully equilibrated with no large-scale order, there would be no arrow, no distinction between past and future. The laws would still hold, but there would be no macroscopic trace of time's direction, no memories, no aging, no special sense of before and after. The fact that we do see an arrow tells us something crucial about the specialness of the early universe. This has deep implications for the question of what came before, because if time's arrow depends on entropy, if the direction of time is tied to the universe's statistical state, then asking what came before the beginning of time may be equivalent to asking what was there before there was any well-defined notion of entropy or before there were any macroscopic states to compare. Perhaps there was a domain in which the concepts of earlier and later simply do not apply. Not because nothing existed, but because the conditions for defining time had not yet emerged. In that case, the word before does not refer to another region on the same temporal line. It points toward a domain where the line itself has not yet formed. In a gentle analogy, it is like asking what is north of the northernmost point on a sphere. North is a useful direction over much of the surface, but at the top, the concept stops. There is no further north. Without leaving the system or changing the geometry, similarly, there may be a sense in which talking about before points beyond the domain where time as we understand it is defined. All of this can feel far removed from everyday experience, yet your own perception offers hints of the underlying structure. You feel that time flows from past to future, but your brain is constantly assembling. This sense from incoming signals, neural processing, takes time. Light reaching your eyes, sound reaching your ears, touch from your skin, all arrive at slightly different moments. Your brain integrates them over short windows to construct a coherent now. Your experience of the present is not a perfectly thin slice. It is more like a small interval blended together into a single continuous feeling. Because of this, you never perceive reality as it is instantaneously. You perceive a processed version, delayed by tiny amounts, smoothed over and interpreted by neural circuits that have their own primitive predictions about what will happen next. This processed now is then connected to stored patterns we call memory to generate a sense of continuity, a narrative, in which you move forward from event to event. In truth, the underlying physical laws are simply relating states. The rich felt sensation of flowing through time is something your brain constructs from those relations, and from the local arrow set by increasing entropy within your body and environment. On longer scales, memory itself depends on irreversibility. Recording information leaves traces, it burns energy, generates heat, increases entropy. If all microscopic processes were perfectly reversible, you could imagine deconstructing memories without cost. But in our actual universe, to remember is to create. Stable physical records, in neural structures, in written text, in digital media. Those records are maintained by the fact that some macroscopic states are more stable than others. That stability is part of what entropy describes. So the existence of beings who experience a directed flow of time, who remember but do not pre-member. The future is deeply connected to the thermodynamic arrow and to the special low-entropy past. This ties our own inner sense of time to the large-scale conditions of the cosmos. Your heartbeat, your thoughts, your aging, all occur within a universe whose entropy is climbing from an initially very special configuration. When you lie back and ask what came before the beginning of time, you are really pressing against several intertwined questions. What is time at the most basic level? Is it a fundamental coordinate built into reality from the start, or is it a parameter we extract from changing states and statistical behavior? Why does time have a direction? Why do we remember the past but not the future? Is that due to deep asymmetries in the laws themselves, or due to boundary conditions on the universe's initial state? If time is emergent from entropy, from thermodynamics, from statistics, then perhaps beyond the earliest stage we can describe, there is only a different kind of order, or no order, from which our familiar time gradually crystallizes, as the universe settles into a regime where entropy makes sense, where macroscopic states can be distinguished, where probabilities can be defined and arrows can be drawn. None of this provides a final answer, but it reframes the question. Instead of picturing a rigid external timeline stretching backward forever, we can imagine a universe in which time is a relational concept, a way of ordering states that arises when certain conditions hold. We can imagine that those conditions may not have held in some deeper domain, and that asking what came before is like insisting on using north and south in a place where only east and west are defined. The question then is not foolish, it is simply misaligned with the geometry of the situation. Recognizing this can be surprisingly calming because it suggests not that there is a forbidden before being kept from us, but that the quest requires new tools, new ideas, a different angle of approach. As you rest with these thoughts, you may notice that they do not demand immediate resolution. They are not puzzles to be solved before sleep. They are more like constellations, patterns in the dark, that you can look at from time to time, each glance revealing a little more about the relationship between fundamental laws, emergent behavior, entropy, and your own sense of moving through existence in the quiet. You can let go of the need to decide whether time is fundamental or emergent, whether reality contains an ultimate before or only a web of relations. You can simply acknowledge that whatever time is, it has brought you to this moment, to this breath, to this intimate contact with questions as old as thinking itself. The universe has grown, cooled, and organized in such a way that beings like you can wonder about the very medium in which they change. There is something deeply peaceful in that realization, even if the answers remain incomplete. So allow your awareness to soften around these ideas: entropy, the arrow, the emergence of time, the possibility that beyond a certain point the word before simply stops applying. Let them float like distant galaxies in a vast mental sky, present but not demanding, and feel that you are free at any moment to turn from them into simple rest, into the unmeasured, gentle flow of your own breathing. Whatever the deepest nature of time may be, it holds you now, in this quiet interval between waking and sleep. In ordinary quantum mechanics, we often picture tiny particles, electrons, photons, atoms, behaving in ways that differ from our everyday intuition. They can be in superpositions, spread out over many positions at once. They can interfere with themselves. They are described not by simple trajectories, but by wave-like objects, called wavefunctions. A wave function assigns to each possible configuration a kind of weight, a complex amplitude, from which probabilities for different outcomes can be derived. When you measure, you never see the whole wave function. You see one result drawn from the distribution it encodes. This is the basic language of quantum theory. Now imagine taking that language and applying it not just to a single particle or a few particles, but to the entire universe, all degrees of freedom, all fields, all possible configurations of geometry and matter wrapped into one enormously rich object. This is the idea behind quantum cosmology. Instead of describing the universe by a single classical history, we describe it by a wave function over many possible histories. Each history has a weight, an amplitude. History does not simply happen. It is selected with some probability from this vast quantum structure. To make sense of such a picture, physicists often turn to a method called the path integral approach. In this view, instead of tracking just one path from an initial state to a final state, we consider all possible paths. Each path contributes with a weight that depends on the action, a quantity constructed from the fields and geometry. The final amplitude is obtained by summing over all these contributions for ordinary particles in a simple potential. This is a mathematical tool for computing probabilities for the universe as a whole. It becomes something deeper, an expression for how likely different global histories are, different possible ways for space, time, and matter to unfold. Within this framework, two physicists proposed a particular idea about the earliest stages of the universe. They suggested that perhaps there is no initial boundary in time in the way we usually imagine, no sharp starting surface, no singular edge. Instead, the histories that contribute are smooth, they have no boundary. In the past, in a certain generalized sense, this is sometimes called the no-boundary proposal. The basic intuition can be approached with a geometric analogy. Imagine the surface of the Earth. If you stand near the equator, you can move north in a straight line. As you do, circles of latitude grow smaller. Eventually, you reach the North Pole. There, the direction north loses meaning. But there is no edge, no sharp boundary. The surface is smooth. There is simply a place where one coordinate stops being useful. Now translate this idea to space-time. Instead of a sharp beginning, where time simply starts, with a boundary that is singular, you imagine a geometry where very early on, the distinction between time and space begins to blur, so that the initial region is more like a rounded cap than a sharp edge, a smooth geometry, without a boundary in time. But with a region where the meaningful notion of time emerges gradually, rather than abruptly. To make this more precise, the proposal uses a mathematical trick. It temporarily treats time as if it were like a spatial direction. This is often described by the phrase imaginary time. The name comes from a specific substitution involving numbers that squared a -1. But the core idea can be understood without the symbolism in many physical systems. Exchanging time for an extra spatial dimension transforms oscillating behaviors into decaying ones. It turns a dynamical problem into a kind of equilibrium problem. In that imaginary time picture, some geometries that would be singular in ordinary time become smooth, closed surfaces without edges. This allows one to define a path integral over all such smooth geometries, weighted appropriately. The no-boundary proposal then suggests that the wave function of the universe is given by this sum over compact, edge-free geometries. When one translates back from imaginary time to the usual description, the universe appears to start in a finite but non-singular way. Time, as we experience it, appears only in a region where the geometry has already transitioned from a fully space-like character to one with a clear temporal direction. In this picture, asking what happened before becomes a little like asking what lies beyond the North Pole. In the Earth analogy, the geometry does not end. It simply changes character. The coordinate we called time no longer points into a physically distinct region. The universe has no boundary. In this generalized sense, not because nothing else exists, but because the meaningful coordinates only cover a certain region, smoothly without requiring an additional before. The cosmos is finite in a way, yet unbounded like a sphere. There is a maximum distance between 2 points on its surface, but no edge where the surface stops. It is natural to ask whether this is just a clever piece of mathematical art or whether it connects to testable physics. The proposal is embedded in the broader framework of quantum cosmology and uses tools that are standard in other areas of quantum physics. The path integral, the idea of summing over histories, the interpretation of complex weights, all of these are familiar techniques. What is unusual is the scale at which they are applied and the fact that there is no external time against which the universe evolves. Time, in these models, is something that emerges within particular histories as an approximate concept linked to the geometry and to the behavior of fields. The wave function of the universe describes, in a sense, all possible four-dimensional spacetimes that satisfy certain conditions. What we call the universe we observe is one branch, one pattern that has high probability weight in that wave function along that branch. Physical clocks can be defined, thermodynamic arrows appear, structure forms, observers arise, but the underlying quantum object is more general. It does not single out a unique notion of before and after. Those notions belong to specific semi-classical histories, where space-time looks smooth and where entropy provides a direction. Because the wave function assigns amplitudes to different histories, it is inherently probabilistic. It offers statements like histories with certain properties have higher probability than histories with others. For example, one might ask how likely it is for the universe to begin in a very rough, highly curved state, compared to a smoother, more nearly uniform one. In certain versions of the no-boundary setup, smooth, nearly homogeneous geometries receive higher weight. In the path integral, this could offer a partial explanation for why the early universe appears so uniform on large scales with only tiny fluctuations superimposed. The proposal does not require a singular beginning, nor does it require a prior region in which time behaved in the usual way. It instead asserts that the most probable histories are those with a finite non-singular geometry that narrows in a way reminiscent of a rounded cap, giving rise to a period in which time gradually becomes a meaningful coordinate. It is important to keep in mind that this is one idea among several in the landscape of quantum cosmology. It is mathematically sophisticated, but also model-dependent. Different choices of what fields to include, what boundary conditions to impose, what measure to use in the path integral can lead to different conclusions. There is ongoing work to relate predictions of such models to observable quantities, for instance, to the spectrum of fluctuations in the cosmic background radiation or to certain statistical features of large-scale structure. If a particular quantum cosmological model were to predict patterns that match observations better than competing models, it would gain support. If it predicted features we do not observe, it would be constrained or ruled out. In this way, even theories about the very earliest stages can in principle be tested. By their indirect consequences, though this process is subtle and requires careful analysis, what makes these ideas scientifically serious is not that they are strange. Many successful theories once sounded strange. It is that they are constructed within a known framework. They strive for internal consistency. They respect the principles of quantum mechanics and general relativity as far as possible, and they aim to connect with observational data. They may ultimately turn out to be incomplete or to require modification, but they are not arbitrary stories. They are specific proposals, expressed in mathematical form. This allows other scientists to examine them, to critique them, to refine them, to compare them against measurements. This is what separates serious theoretical work from unconstrained speculation, even in domains where direct experiments are difficult or impossible. On a conceptual level, treating the universe as a quantum object invites a shift in how we think about beginnings and causation. In classical physics, we often imagine a state of the universe at one time, feeding deterministically into a state at a later time. Cause leads to effect along a well-defined timeline. In quantum cosmology, the focus moves from single trajectories to ensembles of histories weighted by amplitudes. The question is no longer simply what caused the Big Bang, as if there were a prior event inside a larger temporal stage. Instead, we ask, what class of histories are included in the universe's wave function? How are they weighted? Which ones are compatible with the structures we observe? In this view, the birth of the observable universe is not a single instant, cut off from everything else, but a transition region within a broader quantum description where certain approximations become valid, where space-time looks classical, and where the familiar notion of time begins to apply. The idea of a sharp start, a single privileged moment, may be replaced by a fuzzier, more distributed picture, where different histories contribute with different weights, and where the concept of the beginning is at best an emergent feature of semi-classical branches, like the one we inhabit. This does not mean that anything goes. The quantum rules are strict. The amplitudes are constrained by the structure of the action, by the fields included, by the boundary conditions. The challenge is not to invent the wildest possible scenario, but to discover which quantum histories are mathematically allowed and most consistent with what we see. It is a delicate interplay between imagination and discipline, between openness to new pictures and fidelity to established principles. The result is a kind of conceptual quiet, rather than declaring that the universe simply popped out of nothing at a single instant. Such models invite us to think of an underlying quantum state from which our classical world emerges, gradually, with probabilities, not certainties, with smooth transitions, not abrupt walls. As you listen to these ideas, you might notice that they reshape the original question. When you first ask what came before the beginning of time, it is natural to a mind extending backward beyond a marked point. Something must lie to the left of that mark, some cause, some earlier phase, some prior time. Quantum cosmology suggests that the situation may be gentler. Perhaps the mark is not on a line but on a rounded surface. Perhaps the coordinate you call time is only valid on part of that surface. Perhaps before a certain region, the language of earlier ceases to apply. not because there is nothing, but because the underlying description is organized differently. In terms of amplitudes over whole geometries rather than events, strung along a one-dimensional axis, from that deeper level, our sense of time, our classical history, our arrow, all emerge as approximately valid within a limited regime, a regime large enough to contain galaxies, stars, planets, lives, and questions, yet still only a patch in a larger and still mysterious quantum structure. You do not have to resolve how literally. To take these pictures, it is enough, for now, to see that modern physics offers ways to discuss the earliest universe that do not rely on simple images of explosions in pre-existing emptiness or on timelines extending without change into an infinite past. The universe, as described by quantum cosmology, is more subtle, more statistical, more geometric, and more abstract. Yet within that subtlety, there remains a deeply human thread. We are still asking how our universe came to be, why it has the properties we observe, how time itself could arise from deeper rules. The tools are new, the language is refined, but the underlying curiosity is ancient. As you float with these thoughts, allow them to loosen the rigid edges of your original question, to soften the demand for a sharp, single answer, and to replace it with a sense of layered description, of emergent structures, of a universe that may not have a simple storybook beginning, yet still gives rise to a world where beginnings and endings are meaningful at our scale in our lives, within the branch of the wave function we call home, here where time feels real, where memory runs in one direction, where questions are asked and slowly sometimes answered. You can let your mind rest on the edge of this deeper picture, feeling not the full weight of its technical details, but the gentle outline of a cosmos in which even time is part of the story and not the stage, on which it is told. There is a very old intuition that the universe might not have a single one-time beginning, but instead might move in cycles, worlds arising, flourishing, fading, only to give way to new worlds. In cultures across the planet, you find this idea in many forms, cosmic ages that repeat, worlds destroyed by fire or flood or darkness and then remade from what came before. In these ancient stories, there is rarely a final absolute start. There is instead a rhythm of creation and dissolution, an eternal turning of the cosmic wheel. When modern cosmology developed with its picture of a hot, dense early universe and a long history of expansion, it might have seemed that the cyclic idea would fade away, replaced by a single unfolding from an initial state to a final one. But as physicists probed more deeply into the extremes of density and curvature, some of the mathematics began to hint that a new beginning might sometimes be understood as the rebound of a previous phase, a collapse followed by expansion, a contracting universe, passing through some sort of bounce and emerging as a new, expanding cosmos, different in detail but connected to what came before. In this way, the ancient intuition of cycles meets modern attempts to resolve the singularities of classical relativity. One of the most developed frameworks for this kind of picture is called loop quantum cosmology. It is built from a broader program called loop quantum gravity, which attempts to quantize spacetime itself. In that program, the geometry of space is not treated as perfectly smooth all the way down. Instead, areas and volumes acquire a discrete structure. They come in tiny units, small but finite. You can think very loosely of spacetime as being made of quantum grains or loops, intertwined at an unimaginably fine scale. In loop quantum cosmology, these ideas are applied to simple symmetric models of the universe as a whole. Instead of tracking every possible fluctuation, physicists consider an idealized universe that is homogeneous and isotropic, the same on large scales in every direction and at every location. Within that simplification, they write quantum equations for geometry and matter together. When they do, they find that the classical singularity, the point where density would blow up to infinity, is replaced by a phase in which quantum effects of geometry itself provide a kind of repulsion. At extremely high densities, as the universe contracts, the energy density grows, gravity grows stronger, but at some critical density, the quantum discreteness of spacetime becomes significant. Instead of allowing density to become infinite, the quantum geometry acts like an effective pressure, opposing further collapse. The contraction slows, halts, and reverses. The result in the equations is a bounce. A prior contracting branch of the universe transitions into an expanding one. The classical singularity is avoided, replaced by a finite minimum size and a highest but still finite density. In this scenario, the Big Bang as we usually describe it is reinterpreted, not as the absolute beginning of spacetime, but as the aftermath of a quantum bounce. The expanding phase we inhabit is linked to a preceding phase of contraction. It is tempting to ask what that earlier phase would have looked like. Did it have galaxies, stars, observers? Was it similar to our universe or very different? In simple loop quantum cosmology models, the contracting phase is usually taken to be similar in its large-scale symmetry to the expanding one, but that symmetry is an approximation. Realistic cosmology includes inhomogeneities, fluctuations, structures. Extending these quantum ideas to more complex, less symmetric settings is an active area of research. Some results suggest that certain properties of the contracting phase could leave imprints in the expanding phase in the form of altered spectra of primordial fluctuations, tiny statistical differences in the way density variations of different sizes are distributed. Those differences, if large enough, could be detectable in maps of the cosmic background radiation or in surveys of the large-scale clustering of matter in practice. The situation is subtle, many effects can mimic one another, and the quantum gravity modifications must be consistent with all the precise observations we already have. So far, no clear unique signature has been confirmed, but the framework shows how a quantum resolution of the classical singularity can naturally produce a bounce instead of an end. Another family of models explores cycles from a different angle, using ideas from higher dimensional theories. In these pictures, our observable universe is not the whole of reality. It might be a kind of three-dimensional surface embedded in a higher dimensional space. This picture, sometimes called a brane world scenario, arises in certain versions of string theory or related frameworks. Our familiar particles and forces are confined to this three-dimensional brane, while gravity can extend into the extra dimensions within such a setup. It is possible to imagine two such branes existing in a higher dimensional bulk, slowly moving relative to each other over enormously long times. If these branes collide, the energy of their relative motion can be converted into the hot, dense state we associate with the early universe. In this way, a collision between higher dimensional surfaces could play the role of a bang-like event in our three-dimensional world. Before the collision, each brane could be cold, nearly empty, possibly undergoing its own slow evolution. After the collision, a hot plasma of particles and radiation is produced on the brane that we inhabit, which then cools and expands, much like in the standard cosmological picture. If such collisions happen not just once but repeatedly, over cycles of approach, collision, separation, and renewed motion, we obtain a cyclic cosmology. Energetic events occur at each brane collision, repeatedly seeding hot, dense phases, followed by expansion and cooling. One specific version of this idea is called the ekpyrotic scenario. The name comes from a Greek word meaning conflagration, but the physics is not about fire. It is about slow, contracting or approaching phases, in which the universe becomes extremely smooth and flat before a collision. This ekpyrotic phase can help solve some of the same puzzles that inflationary cosmology addresses, such as why the universe is so uniform on large scales and why its spatial geometry is so close to flat. In ekpyrotic models, the smoothing comes not from rapid expansion but from slow contraction with a special kind of energy content. When the branes collide, the energy released generates a hot Big Bang-like state, after which expansion resumes. Later, dynamics in the higher dimensional bulk can cause the branes to move apart, then gradually draw together again, setting up another cycle. The overall picture is one of endless, or at least very long, sequences of contraction, collision, and expansion, each cycle potentially erasing most traces of the one before, leaving only subtle imprints in the patterns of primordial fluctuations. Another cyclical idea comes from a different direction within the same broad tradition of general relativity. A proposal called conformal cyclic cosmology imagines successive aeons of the universe stretching indefinitely into the past and into the future. In this picture, each aeon is an entire universe with its own history, beginning, in some sense, where the previous one ends. The key insight relies on how certain features of the equations look when you rescale the geometry by a factor that changes distances but preserves angles, a transformation called conformal rescaling. At very late times in our universe, if it were to expand without bound, and if all massive particles eventually decayed into massless radiation, the distinction between scales could become less important. In a world filled only with radiation, no particular length scale would be singled out. In that limit, one can sometimes treat the infinitely expanded future as if it were a finite, smooth boundary when expressed in a conformally rescaled geometry. Similarly, the very early universe can be described by another conformally smooth geometry. In conformal cyclic cosmology, these smooth boundaries are identified. The infinity of one aeon is matched to the beginning of the next, without a singular jump. In this matching, certain features, such as patterns in the distribution of gravitational radiation, might carry through from one aeon to the next, leaving potential imprints. In the radiation background of the subsequent universe, some analyses have claimed hints of such imprints in the cosmic microwave background, in the form of unusual circles or correlations. Others have challenged these claims, arguing that the patterns can be explained by random chance within standard cosmology, or that the statistical methods were not sufficiently careful. This debate remains open, but it illustrates how even very speculative models try to connect with observable data by proposing distinctive signatures that can be checked rather than existing only as abstract stories. All cyclic or bouncing cosmologies face a common challenge: entropy. If entropy tends to increase over time from one state to another, then in a universe with many cycles, one might expect entropy to build up, cycle after cycle, eventually reaching a highly disordered state in which further cycles would no longer resemble ones earlier in the sequence. This is often called the entropy problem. In cyclic models, different proposals address it in different ways. In some bouncing scenarios, it is suggested that entropy is diluted during very long phases of expansion between bounces, so that when the universe contracts again, only a tiny fraction of the previous entropy remains relevant. In others, it is argued that certain degrees of freedom do not contribute to the perceived entropy in the same way, or that the notion of entropy must be generalized in the presence of changing geometry. In brane collision models, some of the entropy might be radiated into hidden dimensions or into degrees of freedom that do not affect the observable universe. In conformal cyclic cosmology, the asymptotic future is envisioned as a regime where the usual clocks and scales lose meaning, perhaps allowing a kind of reset when rescaled into the next aeon. These ideas are subtle and often controversial, because entropy is deeply tied to probabilities and to the arrow of time. Any proposed mechanism for recycling the universe must handle entropy with great care to avoid contradictions with what we observe about thermodynamics in each cycle. From an observational standpoint, cyclic and bouncing cosmologies are being probed primarily through their implications for the primordial universe. If a bounce occurred, or if there was an ekpyrotic phase, or if structures from earlier aeons can leak into later ones, then the statistical distribution of temperature fluctuations in the cosmic microwave background might differ slightly from the standard predictions of simple inflationary models. There might be specific non-random patterns in the way hot and cold spots are correlated. There might be subtle differences in the behavior of fluctuations at very large angular scales, or small ones. Precise satellites have already mapped the background with exquisite detail. Future missions will refine these maps even more. Similarly, patterns in the distribution of galaxies and in the spectrum of primordial gravitational waves, if detected, could favor one class of scenarios over another. So far, the data are broadly consistent with the simplest versions of inflationary cosmology, but they do not yet exclude all variants of bouncing or cyclic models. Many of those models can be tuned to mimic the successful predictions of inflation while differing in more subtle behaviors that remain on the edge of detectability. This means theoretical and observational work continue in parallel, gradually tightening constraints on what kinds of cycles, if any, are compatible with our universe. Throughout all of this, a gentle truth remains: none of the bouncing or cyclic cosmologies currently enjoys the same level of empirical support as the basic picture of a hot expanding universe with a well-measured age and a well-tested history. They are extensions built on top of that framework. They aim to answer further questions, such as what resolves the Big Bang singularity, whether time can be extended beyond the earliest moments, whether the universe has a prehistory in a prior contraction or a prior aeon. They are mathematically serious. They are motivated by real issues in gravitational physics and cosmology, but they are not yet confirmed. This status does not make them worthless. It simply places them in the correct category of carefully constructed possibilities, awaiting clearer tests. You can hold them lightly as examples of how physics can explore the concept of before without making claims that exceed the evidence. If you imagine the universe as breathing gently, in and out, expanding, then contracting, or as moving through cycles of aeons, each giving rise to the next, you are visualizing ideas that sit at the intersection of mathematics, observation, and very old human intuitions. Yet it is equally possible that our universe's history is not cyclic, that the bounce is replaced by something else, or that time in any familiar sense does not extend beyond the domain. We can currently describe the value of studying cyclic models is not only in the chance that one of them will be exactly right, it is also in the way they force us to sharpen our understanding of singularities, of entropy, of boundary conditions, and of what it truly means to ask, how did it all begin? As you let these possibilities drift through your mind, you do not have to decide which, if any, feels most compelling. You can simply notice that within the language of modern physics, there is room for universes that bounce, for universes that cycle, for universes that emerge from prior phases or prior aeons, and there is also room for universes whose earliest moments remain beyond our present concepts. In every case, the question of what came before the beginning of time becomes more nuanced, less like tracing a straight line back to a single point and more like exploring a varied landscape of possible histories, possible geometries, possible ways for time itself to behave. And from within that landscape, here you are, in one particular universe, at one particular moment, letting your thoughts wander across cycles and bounces, while your body lies still, rooted in a single, quiet now, between whatever came before and whatever comes next. There is a moment in the story of modern cosmology when the simple picture of a universe that just expands and cools proves not quite enough, not because it is wrong, but because, when we look very closely, we find puzzles about smoothness, about flatness, about how regions of the universe that should never have communicated seem to share the same conditions, as though they once were much closer than they appear today. It was in response to these puzzles that the idea of cosmic inflation was born, a brief period of extremely rapid expansion in the very early universe, faster than the ordinary expansion we speak about when we describe galaxies moving apart. This rapid phase, if it occurred, could help explain several otherwise puzzling facts in a simple, coherent way. One of those facts is the remarkable smoothness of the cosmic microwave background. When you look at that ancient light coming from regions of the universe separated by great distances, you find that its temperature is nearly the same everywhere, differing only at the level of tiny fluctuations of a few parts in 100,000 in ordinary, non-inflating expansion. These far-apart regions have not had time to exchange light signals. Since the Big Bang, they are outside each other's causal reach, and yet they have almost identical conditions. This is known as the horizon problem. Inflation addresses it by suggesting that before the rapid expansion, these regions were much closer together within a single, causally connected patch. They could equilibrate, share information, reach a nearly uniform state. Then inflation stretches this patch to enormous size, so that regions, now far apart, once shared the same thermal history, the same physical conditions. Their similarity becomes a natural consequence of that prior proximity. Another puzzle is the observed flatness of space on large scales. In general relativity, the universe's spatial geometry can be positively curved like the surface of a sphere, negatively curved like a saddle, or very close to flat where triangles behave almost as in Euclidean geometry. The density of matter and energy helps determine which of these possibilities applies. In standard, non-inflating cosmology, the state in which the universe is nearly flat is unstable, Small deviations from the critical density grow with time, leading either to a strongly curved universe that recollapses or to one that expands so rapidly that structure cannot easily form. Yet when we measure the large-scale geometry, we find it extremely close to flat, as if the density were tuned very precisely to the critical value. Inflation provides a mechanism that drives the universe toward flatness. During the rapid expansion, any initial curvature is stretched out, diluted, much as the surface of a balloon appears flatter and flatter to a tiny ant walking on a small patch. As the balloon is inflated, after enough expansion, any local region will look almost perfectly flat. No matter what the initial curvature was, the observed flatness becomes a consequence of extended inflation, rather than a delicate coincidence of initial conditions. A third role is played by inflation in the origin of cosmic structure. During inflation, quantum fluctuations in the fields that drive expansion are constantly generated on very small scales. Under ordinary circumstances, these would remain microscopic, but because space is expanding so rapidly, fluctuations can be stretched from the quantum realm to astronomical distances. A perturbation that begins as a tiny ripple in a field over a very small region can be carried by the expansion to scales much larger than the horizon, freezing in as a small variation in density. Once inflation ends and the universe reheats, these tiny differences in energy density provide seeds for later structure formation. Regions that are slightly denser attract more matter over time, growing into galaxies, clusters, and the web-like network we observe today. In this way, inflation transforms vacuum fluctuations into the blueprint of the large-scale universe. The statistical distribution of these fluctuations can be calculated and compared with observations of the cosmic microwave background and large-scale structure. So far, many inflationary models are consistent with the data, though details matter, and not every simple version survives close scrutiny. Up to this point, we have described inflation as a phase that begins at some time, then ends everywhere, roughly at once, leaving behind a hot, dense universe like the one described by the standard Big Bang model. But in some versions of inflation, the story is more subtle. The process does not end everywhere at the same time. In fact, it may never end. Globally, inflation depends on the behavior of a field, often called the inflaton, whose energy density drives the rapid expansion. As long as this field sits high enough in its potential, space expands at an accelerated rate. In some regions, quantum fluctuations can kick the field down the potential, ending inflation locally and converting energy into particles and radiation. In those places, expansion slows and the universe enters a hot, dense phase. In other regions, fluctuations push the field back up or keep it from rolling down long enough that inflation continues. In those patches, space keeps expanding at an enormous rate. This combination of local endings and ongoing inflation elsewhere leads to what is called eternal inflation. In eternal inflation, the global spacetime is a patchwork of regions where inflation has ended, separated by regions where it continues. The inflating regions grow exponentially, creating more and more volume, even as small islands of post-inflationary space nucleate within them. Those islands can be thought of as bubble universes. Each bubble is born when inflation ends locally. Inside a bubble, the physics can resemble our familiar Big Bang story, a hot, dense phase, followed by expansion, cooling, structure formation. Outside the bubble, inflation continues, driving more expansion and creating still more opportunities for new bubbles to form. If the process continues, without bound, the overall structure becomes a multiverse, an ever-expanding inflating background dotted with countless bubble regions, each one potentially a universe in its own right. Our observable cosmos would be one such bubble, one pocket inside a much larger inflating space. In many formulations of inflation, the properties of each bubble are not identical. They depend on how fields settle into different configurations after inflation ends locally. In certain high-energy theories, such as some versions of string theory, the space of possible low-energy states is thought to be vast. There can be many different ways to compactify extra dimensions, many ways. Fields can acquire masses and interaction strengths. The result is sometimes called a landscape of vacua. Each vacuum state corresponds to a particular set of physical constants, particle spectra, and low-energy physics. In eternal inflation, different bubbles can end up in different vacua, populating the landscape with regions where the effective laws of physics differ in detail. Some bubbles might have very different values for the cosmological constant, the parameter that controls the acceleration of cosmic expansion. Others might have different strengths for fundamental forces, different particle masses, or different patterns of symmetry breaking. Only a subset of these vacua would support long-lived galaxies. Stable chemistry and complex structures, others, might expand too quickly, for matter to clump or recollapse too rapidly, for stars to form. In such a picture, the fact that we find ourselves in a universe with conditions suitable for life is not explained by a single fine-tuning of unique laws, but by the fact that observers can only arise in those bubbles where conditions allow them. This is sometimes referred to as an anthropic selection effect, not in the sense that mind shapes reality, but in the sense that observations are conditional on the existence of observers. These ideas are part of what makes eternal inflation in the multiverse controversial. On the one hand, they arise naturally in certain inflationary models. They are not arbitrary additions. On the other hand, testing them is difficult. By construction, regions beyond our bubble are separated by inflating space, expanding faster than light signals can cross. There is no simple way to travel from one bubble to another or to receive messages from regions where inflation still proceeds. And yet, proponents argue that the multiverse picture can still be scientific if it leads to statistical predictions for distributions of observable quantities. For example, the distribution of cosmological constants across the landscape might favor some values over others. Combined with selection effects, this could lead to a probability distribution for what observers should expect to measure. If our measured value is very typical within that distribution, the framework gains support. If our measured value is very atypical, it loses support. Even though we cannot see other bubbles, we can compare the predictions of competing models for what observers should see in their own region. Still, this approach is subtle. It depends on how one defines probabilities. In an eternally inflating multiverse, where volumes can be infinite, there is a so-called measure problem. Different ways of regulating infinities and counting regions can give different answers to questions like, what fraction of observers see a certain property? Much of the debate around eternal inflation revolves around this issue: how to define a measure that yields stable, meaningful predictions without arbitrary choices. There is also a philosophical unease. For some, in appealing to a vast ensemble of unobservable regions to explain the properties of our own, they worry that this moves physics too far from direct testability, too close to speculative metaphysics. Others respond that theories have always had components we cannot directly access. At first, what matters is not whether every element of a theory is presently observable, but whether the theory as a whole is constrained by data and yields predictions for quantities we can measure. From that perspective, eternal inflation is acceptable if it is part of a framework that predicts, for example, the spectrum of primordial fluctuations, the amplitude of gravitational waves, or other observables in ways that can be checked against experiments. If it fails those checks, it will be disfavored. Regardless of how appealing or unappealing the multiverse picture may be, as with any scientific idea, the ultimate judge is consistency with observation, not aesthetic preference. When it comes back to the question of what came before the beginning of time, eternal inflation offers a distinctive twist. In a simple Big Bang story, the hot, dense early universe feels like a starting point. Even if the singularity is eventually smoothed by quantum effects, there is still a sense of first moment. In eternal inflation, our hot, dense beginning is local, within a larger ongoing process. The inflating background could extend far into what we would call the past, producing bubbles long before our own, and it could continue far into what we call the future, creating new bubbles long after our region has cooled and thinned. In some models, inflation has no beginning in cosmic time. In others, it may itself begin from some prior state or some quantum nucleation event. The question of before then shifts from our local Big Bang to the onset of the larger inflating state or to the deeper theory that underlies inflation. In either case, our Big Bang ceases to be the ultimate origin. It becomes a transition from one phase to another, a local event in a broader tapestry. For some, this can feel deflating. If there are countless bubbles, countless regions, perhaps with different physics, does that make our universe less special, less meaningful? But from another angle, it can be the opposite. Even if there are many regions, our experience of this one is still unique to us. We still live on a particular planet, around a particular star, in a particular galaxy, within a particular bubble. The fact that there could be other regions with other values of physical constants does not diminish the reality of this one, nor does it erase the deep structure of the laws we have discovered within our own universe. Those laws still describe how matter and energy behave, how stars shine, how life can arise. The possibility of a landscape adds another layer. It suggests that the laws we see might themselves emerge from a deeper pattern in a larger ensemble. The sense of wonder can expand to include not just one cosmos, but a wider space of possibilities in which our cosmos is one expression of underlying principles. We are still trying to understand whether eternal inflation and the multiverse are ultimately the correct description of reality remains uncertain. They are compelling, in some respects challenging. In others, they are active topics of research with new variants, new constraints, and new ideas appearing as our understanding of high-energy physics and cosmological data improves. It is entirely possible that future observations will favor simpler pictures or point toward a different mechanism for the earliest universe. It is also possible that some version of eternal inflation will survive and be woven into a larger theory of quantum gravity and cosmological origins. For now, they serve as one example of how modern physics can stretch the notion of before the beginning beyond the intuitive image of a single starting line into a more complex and layered structure where beginnings are local, not global, and where time may extend far beyond the horizon of our own bubble. As you let this sink in, you might notice that the details of potential landscapes and measures matter less for your rest than the general feeling of openness. Our best theories do not yet provide a final answer to what, if anything, preceded our hot, dense beginning. But they show us that the question itself can be framed in many ways: singularities, bounces, eons, eternal inflation. Each framework offers a different way to think about before, and each one is constrained by the same underlying commitment to match what we observe here and now. In this sense, you can feel a quiet confidence, not that we know the ultimate origin story, but that we are learning how to ask better questions, step by step, theory by theory, observation by observation. And while that process continues, you are free in this moment to set the details aside, to feel only that you live in a universe whose beginnings are still being deciphered, whose structure is rich enough to support galaxies, stars, life. And late at night, a mind wondering gently what came before the beginning of time. At the scales of everyday life, matter feels solid, localized, made of particles, tiny beads that move through space and interact in familiar ways. But when physicists push their theories to higher energies, shorter distances, and more extreme conditions, the particle picture begins to strain at those scales. A different idea becomes useful. Instead of imagining point-like objects with no spatial extent, some theories replace them with tiny vibrating strings, one-dimensional objects whose different patterns of vibration correspond to the different particles. We observe an electron, a photon, a quark. In this view are not fundamentally different species. They are different notes played on the same underlying string. Change the vibrational mode, and you change the mass, the charge, the spin, the observed properties of what appears as a particle at lower energies. This string-based description does something important. When gravity is included, point particles interacting via quantum rules lead to severe difficulties at extremely small distances. The probabilities of certain processes blow up in ways that are hard to control. Extended objects, such as strings, smear out interactions over small distances, softening some of the infinities. Without going into the detailed mathematics, the essential point is that tiny strings behave more gently than points at the highest energies. This makes them attractive candidates for unifying all forces, including gravity, within a single quantum framework. In the string picture, the graviton, the hypothetical quantum of the gravitational field, is just one vibrational mode among many. Gravity is built in from the start, But strings bring with them a striking consequence. They do not naturally live in a space-time with only 3 dimensions of space and 1 of time. The consistency of the theory requires more spatial dimensions. Depending on the precise version, there can be 9 spatial dimensions, or 10, or even more. This sounds immediately at odds with experience. We seem to move freely in 3 spatial directions, left and right, forward and backward, up and down. There is no obvious access to extra directions. So if they exist, they must be hidden in some way. One way is through compactification. Imagine a garden hose viewed from far away. It looks like a one-dimensional line. You can move along it in one direction, but when you zoom in, you see that it has thickness around its circumference. You can move both along the hose and around it. The circular dimension is compact, curled up so small that from a distance it is effectively invisible. In string theory, the extra spatial dimensions can be compactified into tiny shapes, curled up on scales far smaller than any we can probe with current experiments. Strings can vibrate and move in these hidden dimensions as well as in the extended ones. The detailed geometry of the compact space helps determine which vibrational modes exist and therefore which particles and forces appear in the lower dimensional world. We observe a picture. In mind, physicists began to ask, what happens if we use strings and their extra dimensions to describe the universe as a whole, not just individual particles, but the entire cosmos from its earliest moments to later times? String cosmology is the name given to this effort. One of its intriguing themes is the idea that the familiar expanding universe might have been preceded by a contracting phase in which the stringy nature of matter and space-time becomes important in ordinary general relativity. A contracting universe tends to form a singularity. As distances shrink, densities grow, curvature increases, and the equations break down. String theory offers additional structure that may change this behavior. One key idea is duality, a relationship between seemingly different descriptions that turn out to be physically equivalent. For example, in some string setups, a spacetime with one compact dimension of a very small size can be equivalent to a spacetime with that dimension much larger. The physics at radius r can be mapped to physics at radius inversely proportional to r. Very small and very large are not truly distinct. They are related by a duality transformation. This hints that as the universe contracts and some dimensions shrink, their physics might be mirrored by an expanding description on the other side of a minimal size. Instead of crashing into a singularity, the universe could reach a regime where a dual description takes over, turning contraction into expansion without infinite densities. In this way, the Big Bang could be reframed as a transition from a prior contracting branch to our expanding one, mediated by stringy dualities and quantum effects. Specific models have been proposed in which the universe undergoes such a pre-Big Bang phase, contracting in a way controlled by string fields and their interactions. During that phase, certain modes can be amplified, seeding fluctuations that later become the seeds of cosmic structure. At some critical point, the description in terms of classical geometry becomes inadequate and a fully stringy treatment is required. But if a duality allows us to pass through to an expanding branch, the singularity is replaced by a bounce-like transition. The details depend on which fields are included, which dualities are invoked, and how higher-order corrections are handled. This is a technically rich but still incomplete area of research. The broad message is that the extra structure in string theory provides new mechanisms for connecting, contracting, and expanding phases without the pathologies of pure classical relativity. Another family of string-inspired cosmological pictures returns to the idea of branes, higher dimensional surfaces on which strings can end, or along which they move. In some constructions, our observable universe is modeled as a three-dimensional brane embedded in a higher dimensional bulk. Other branes can exist parallel to ours, separated along the extra dimensions. The dynamics of these branes can give rise to cosmological events. If two branes approach and collide, the energy stored in their motion and in the fields between them can be released as a burst of particles and radiation on the branes. To observers living on one of those branes, this event could appear as a hot, dense beginning, very much like a Big Bang. In this way, brain world cosmology offers a geometric reinterpretation of the bang, not as the creation of space-time from nothing, but as an interaction between extended objects in a higher dimensional setting. Before the collision, each brain can be relatively cold and empty. Afterwards, it is filled with a hot plasma of fields and particles. That then evolves. According to the usual rules of cosmology, as time passes, the brains can separate, move apart, stretch, and later, under certain conditions, be drawn together again, setting up the possibility of repeated collisions and repeated hot phases. This connects brain cosmology to cyclic scenarios, where each collision generates a new era of expansion and structure formation. While the higher dimensional motion provides a global rhythm for the overall evolution, from the string viewpoint, these brain-based models are natural because strings can attach to brains. Different types of strings, different brains, and different compactification shapes lead to different low-energy physics. The small-scale geometry of the extra dimensions and the configuration of brains determine what fields and interactions exist on our three-dimensional slice. Thus, cosmological evolution in the higher dimensional bulk can change the effective laws experienced by observers on the brain in principle. This means that early brain interactions could have left imprints in the statistical properties of cosmic fluctuations in the cosmic microwave background or in the distribution of galaxies. Some models predict specific non-Gaussian features or particular patterns that differ from those expected in simple inflation observations, have constrained many possibilities, but have not yet eliminated all such scenarios. The search continues for distinctive signatures that might point toward a brain-based origin for our hot beginning. Another concept that emerges from string theory and related areas is holographic cosmology. It grows out of a surprising relationship between theories in different numbers of dimensions. In certain cases, a theory of gravity in a higher dimensional space can be equivalent to a quantum field theory without gravity living on the boundary of that space. This is sometimes captured by saying that the boundary theory is holographic. It encodes the bulk physics, the way a two-dimensional pattern on a hologram plate encodes a three-dimensional image. In the most studied examples, this correspondence relates a gravity theory in a space with negative curvature to a conformal field theory on its boundary. The details are specific, but the broader idea has inspired work on applying holographic reasoning to cosmology. In a cosmological context, one attempts to describe aspects of an expanding universe in terms of a lower dimensional theory, defined on some notional boundary, perhaps at very early or very late times. In some proposals, the initial conditions of the universe are encoded in a holographic dual, a quantum system without gravity, whose states map to possible cosmological histories. From that viewpoint, of the beginning is reframed as a question about the behavior of the dual theory in its own time parameter. This can offer new ways to think about singularities and about what it means for the universe to start. If the dual theory is well defined for all times, then some aspects of the bulk cosmology may be extendable beyond what classical geometry would allow. The precise mappings are technically demanding, and different holographic cosmology models make different choices about what plays the role of the boundary and what symmetry structures are involved. But the unifying theme is that higher dimensional beginnings might be encoded in lower dimensional quantum data, providing another channel through which the notion of before can be examined without relying solely on extrapolating classical spacetime to its limits. With all of these pictures, strings, extra dimensions, brains, dualities, holographic boundaries, it is natural to ask how secure any of this is. The honest answer is that these ideas remain speculative in the sense that they have not yet been confirmed by direct experimental evidence of strings or extra dimensions or holographic duals. We do not yet have measurements at energies high enough to probe strings directly. We have not detected particles escaping into extra dimensions, nor have we observed clear imprints in cosmological data that require a stringy explanation. Instead, we have a framework with remarkable internal consistency, rich mathematical structure, and deep connections to known physics, but with many possible realizations, many possible shapes for the compact dimensions, many possible brain configurations. Each realization leads to a different spectrum of low-energy physics, our universe must correspond to one of these, if the framework is correct. But we do not yet know which one. The space of possibilities is vast. This is sometimes called the landscape problem. Given this uncertainty, why do these ideas matter scientifically? Why devote effort to string-inspired cosmology? One reason is that the early universe is precisely the regime where a quantum theory of gravity is needed. Classical general relativity and quantum field theory each work well in their domains, but at extremely high densities and curvatures. They must be combined. String theory is one of the leading candidates for such a unified framework, even if the exact details of compactification or brane dynamics are not yet fixed. Studying cosmology within this setting helps us understand what kinds of behavior are generic in a quantum gravity theory. Do singularities persist or are they resolved? Do bounces or phase transitions occur naturally? Can the universe have a prehistory that is described within the same theory, rather than requiring a separate set of assumptions? Another reason is that string-based models provide concrete laboratories for testing broader ideas, such as the holographic principle or dual descriptions of cosmological evolution. By working out specific examples, physicists can see where their intuitions hold and where they fail. This in turn feeds back into more general thinking about entropy, information, and the structure of space-time. A third reason is mathematical consistency. The more one requires of a theory, the fewer possibilities remain, demanding that a model be consistent with quantum mechanics, with the symmetries of relativity, with anomaly cancellation, with stability conditions, and with existing experimental bounds, eliminates many naive constructions. String theory offers a tightly constrained arena in which to build models. The search for a cosmology that is both string-consistent and observationally viable is a way of using empirical reality to guide choices within a rich mathematical space. Even null results where particular models are ruled out are valuable. They tell us where the theory fails to match the universe, and thus where further refinement or a different approach is needed from the perspective of someone lying awake, wondering what came before time. All of this can feel distant. The vocabulary of strings and branes may seem far removed from the quiet rhythm of breathing, yet it is part of the same human impulse to push our theories into regimes where intuition falters, to ask whether the deep structure of reality contains more layers than our senses reveal, whether the bang was singular or a transition within a higher dimensional dance, whether the initial state of the universe is encoded in some dual description on a boundary or in the shape of compact spaces too small to see. Even if these particular frameworks turn out to be incomplete, the questions they sharpen will survive. What replaces them will still need to address singularities, to reconcile quantum theory with gravity, to explain why our universe has the properties it does, and to clarify whether there is a meaningful sense in which something came before the domain we call the beginning. For now, you can let these ideas drift like faint patterns on the edge of perception, strings vibrating in hidden dimensions, branes gliding through a larger space, colliding and giving rise to hot beginnings, dualities relating contraction to expansion, holographic maps encoding bulk histories in boundary data. You do not need to hold the technicalities, only the gentle sense that modern physics has tools to imagine beginnings that are not sharp, absolute edges, but transitions across deeper structures. And while those tools are still being honed, still being tested, they already reveal something calming. The universe may be more intricate than the simple pictures we first draw, yet within that intricacy there is coherence, a search for internal consistency, a demand that stories be written in the language of equations that work together without contradiction. It is in that search for mathematical harmony, constrained by observation, that many physicists place their trust as they inch closer to understanding what, if anything, might have preceded the time we can describe. As you rest, you can borrow a little of that calm, knowing that it is acceptable for the deepest questions to remain open. For now, they are being carried by people who spend their days exploring strings, branes, and holograms, while you, in this quiet moment, can simply float on the surface of the mystery, letting the unknown be part of what makes the universe quietly beautiful. There is a word that seems so simple and yet becomes slippery. As soon as you look at it closely, that word is nothing. It appears to mean the absence of everything. No matter, no radiation, no fields, no space, no time, no laws, just nothing. But when physicists talk about nothing, they almost never mean something so absolute. In practice, the nothing of physics is usually a very particular kind of something, a carefully defined state of a system with structure, rules, and measurable properties. It is here that language and intuition begin to diverge, and where the question of what came before time runs into the question of what we even mean by before or empty or nothing at all. In quantum field theory, our best description of matter and forces, the fundamental ingredients, are not particles, but fields. Spread throughout space, every type of particle corresponds to a field. Electrons, quarks, photons, each has its own field. Even when there are no particles present, those fields still exist. They can be in their lowest energy state, their quantum vacuum state. To a first approximation, this vacuum is what a physicist might call empty space. No excitations, no real particles, just fields, sitting quietly in their ground configuration, but the word quietly is misleading. Even in this lowest state, quantum fields cannot be exactly zero. They fluctuate, they jitter, with what are called zero-point fluctuations, tiny, irreducible variations, in their values spread through all of space. These fluctuations are not added on top of nothing. They are built into what nothing means. In this formalism, the vacuum is not a blank, featureless void. It has energy, it has correlations, it can polarize in response to boundaries or external fields. In some setups, it can even exert forces, as in the Casimir effect, where two closely spaced plates experience an attractive force because the vacuum modes between them are restricted relative to those outside. In this way, the quantum vacuum is more like a restless medium than an empty container. It is a stage with permanent structure on which excitations appear as particles and vanish again. This has consequences for cosmology. In certain models, a region of space in a particular vacuum state can be unstable. It can tunnel to a different state with lower energy. In that transition, energy can be released into particles and radiation, heating the region and changing its properties. From one perspective, this can look like a universe emerging from nothing, if you call the initial vacuum nothing, but we can see that this is not an absolute nothing. It presupposes a pre-existing space-time with quantum fields. It presupposes the framework of quantum mechanics and whatever deeper laws define the landscape of possible vacua. So when a popular description says that universes can arise from nothing by quantum fluctuations, what it really means is that within a background of quantum fields governed by known laws, regions can transition from one state to another with dramatic consequences for the matter content and geometry inside them. Nothing in that slogan is a sophisticated, structured vacuum, not the complete absence of all reality. Vacuum energy, the energy associated with the quantum vacuum, plays another role. In cosmology, Einstein's equations relate the curvature of space-time to the energy and momentum present in it. A non-zero vacuum energy acts like a uniform energy density spread evenly throughout space with a peculiar pressure, negative, relative to ordinary matter. When you plug this into the equations, it leads to accelerated expansion. The more such energy there is, the faster the expansion accelerates. In our universe, observations of distant supernova and of the cosmic microwave background indicate that the expansion is indeed accelerating, as though space itself were filled with some form of dark energy or vacuum energy, often modeled by a term called the cosmological constant. Its exact nature is not fully understood, but one possibility is that it is simply the energy of the vacuum, a constant energy density associated with empty space. If that is so, then even in regions devoid of matter and radiation, the vacuum itself shapes the geometry, driving expansion over cosmic times. Again, nothing is not inert, not neutral. It has dynamical effects on the fabric of space-time. This raises a profound question. If a universe can appear as a quantum fluctuation of a vacuum, or if its expansion is driven by vacuum energy, where did that vacuum come from? Where did those fields and their laws originate? You might imagine a prior state more empty than the vacuum, a state with no fields, no space-time, no laws. But at that point, the language of physics begins to fail. Physics, as a discipline, describes patterns within a given framework. It assumes a set of variables, a set of rules, dynamics, symmetries, a concept of measurement. Even when we talk about the creation of particles from the vacuum, we are always working within some predefined structure. The question of why that structure has the form it does is not answered by the theory itself, at least not yet. Sometimes new theories partially answer old why questions by showing that a particular feature emerges naturally from deeper principles. For example, symmetries can determine allowed interactions, consistency conditions can fix dimensions, or particle content. But there is always some level at which we must say, these are the rules of the game within this model. We can explore their consequences, we can test them against observation, we can compare competing rule sets. But the question of why reality has these rules rather than others may not have a further physical answer. It may be that at some point the why becomes a question about existence itself, not about dynamics within an already existent stage. Another subtle distinction concerns space-time itself. In everyday thought, we imagine space as emptiness, a container into which matter can be placed, a background that would still exist even if all contents were removed. In general relativity, this picture is altered. Space-time is not separate from matter and energy. Its geometry responds to what is in it. Curvature is tied to energy and momentum. Even in regions without matter, space-time can have structure. It can be curved. It can support waves, gravitational waves, that carry energy through empty regions. So when we say no matter, we are not automatically saying no space-time. The stage can have geometry even when there are no actors on it. In some approaches, space-time itself is emergent, arising from more fundamental degrees of freedom, such as entanglement patterns in an underlying quantum system. In those views, empty space is not a pre-given arena, but a kind of collective state. Of more basic constituents, removing all particles does not eliminate those constituents, it simply changes how they are arranged. So once again, nothing, defined as no particles, is not the same as nothing, defined as no structure at all. When cosmologists ask whether the universe could have come from nothing, they often mean from a state with minimal excitations. A vacuum, or a symmetric configuration of some underlying system. In certain quantum cosmology models, one can write a wave function for the universe, describing the probability of different geometries and field configurations. In some proposals, the amplitude for the universe to arise with small size and simple geometry is non-zero. The universe can appear as a quantum event without prior classical time, in which it evolves. In such descriptions, time itself can be emergent. Within particular branches of the wave function, you can have a timeless underlying equation from which different histories with internal time notions emerge, but the nothing from which these histories emerge is still a mathematical object, a state or a solution of a deeper theory, defined in a configuration space of geometries and fields. It is not the absence of all law and structure. It is a precise technical concept disguised in a simple word. If we try to push past this, to imagine a true absolute nothing, we run into conceptual trouble. In a state with no space, no time, no fields, no laws, there is no notion of evolution, no before or after, no processes, no probabilities, no transitions. There is not even a stage on which something could begin. In that sense, a genuine nothing cannot undergo a change, because change requires time and some kind of entity to change. When people say maybe the universe came from nothing, they are often using the word nothing to mean no classical matter, no familiar space, just a quantum gravitational something we do not yet fully understand. From a strict standpoint, that is still something, a structure with rules. The full story of what that structure is and how our observed universe emerges from it is still being worked out. This is where the boundary between physics and philosophy becomes visible. Physics is very good at answering how questions. Given certain starting conditions and laws, how will a system evolve? What patterns will appear? What observables will we measure? It is also good at many what questions, the relationship between certain quantities. What symmetries does a system have but the why of ultimate existence? Why there is something rather than nothing, in the absolute sense, may not be reducible to a physical calculation. That does not mean it is meaningless. It simply means that our current frameworks are not designed to address it. They assume their own domains in which objects and rules are already present from within those domains. We can ask whether earlier phases of the universe involved a vacuum state, whether vacuum energy can drive expansion, whether quantum events can create regions with different properties. But we may have to accept that the step from absolute non-being to being, if that phrase even makes sense, is not accessible. To the methods we use in physics, at least not yet. This realization leads naturally to humility. When we talk about nothingness, in cosmology, we can be precise about what we mean by a vacuum state, by zero-point fluctuations, by empty spacetime. We can explore models in which the universe arises from such states. Through quantum processes, we can calculate probabilities. We can compare their predictions to observations, and in doing so, we can push back the boundary of the unknown. But beyond that boundary, there may always remain questions whose answers are not encoded in data or in equations. When you hear a confident phrase like, "The universe came from nothing," it is worth remembering that the nothing in that sentence is a term of art, not an absolute. It conceals a structured backdrop of fields or wavefunctions or laws. Our true ignorance lies one level higher in the origin of that backdrop itself. For a listener, late at night, this can actually be calming. Instead of feeling that everything must be fully resolved, you can allow some layers to remain unfinished. You can picture the quantum vacuum not as a bleak void, but as a sea of subtle fluctuations, a ground state alive with potential. You can imagine space-time not as empty nothing, but as a flexible fabric curved by energy, perhaps emergent from deeper patterns. You can see that even when physicists speak of nothing, they are really speaking of very specific somethings, defined carefully within their theories. Beyond those somethings, beyond the frameworks and formalisms, there is a wider unknown into which our current equations do not yet reach. That unknown is not a failure. It is part of what makes the universe endlessly interesting. It is the dark sky in which new ideas might someday appear. Like stars, as you breathe, you might let nothing soften from an absolute into a spectrum. At one end, the emptiness of a quiet room at night; at another, the quantum vacuum of fields without particles; beyond that, the possibility of deeper structures that give rise to space-time itself; and beyond even those questions that our language is not yet equipped to phrase cleanly. The important thing for this moment is that you do not need to resolve them. You can simply rest with the recognition that the word nothing carries more than it seems, that emptiness is rarely truly empty, and that the journey toward understanding what came before the beginning of time will always run through careful attention to what we mean by something, by nothing, and by the fragile line we draw between the two. For now you are allowed to let that line blur, to feel yourself held gently between presence and absence, between knowing and not knowing, between the fullness of the universe and the quiet spaces we call empty, even though they are already filled with possibility. There is a direction to almost everything you experience. Morning flows into afternoon, children grow into adults, memories accumulate behind you, possibilities stretch out in front. You never see a broken glass leap from the floor and reassemble itself. You never watch smoke gather back into a candle. The world around you unfolds in a particular way, from past to future. We call this the arrow of time. In the equations of fundamental physics, this arrow is strangely absent. Most of the basic laws look the same. If you imagine running time backwards, if two particles collide and scatter, you can reverse the motion and obtain another process that still obeys the same equations. Electric and magnetic fields, quantum amplitudes, gravitational interactions are mostly indifferent to the direction in which you label time forward or backward. The mathematics does not care, but your life clearly does. There is a felt difference between remembering and anticipating, between ashes and logs, between melted ice and frozen water. So where does that difference come from? If it is not obvious in the microscopic rules, the central concept that captures this is entropy, a measure of how many microscopic arrangements correspond to the same macroscopic state. Imagine a box of gas. You do not track every molecule. You describe its overall temperature, its pressure, its volume, its density. But for any given set of such bulk quantities, there are an enormous number of ways The individual molecules could be arranged. Each arrangement is a microstate. The coarse description is a macrostate. Entropy counts how many microstates fit under that coarse description, more precisely, with the logarithm of that number. Low entropy means few microstates. High entropy means many. In everyday terms, low entropy is more ordered. High entropy is more disordered. Not because disorder is a moral category, but because disordered-looking states can be realized in far more microscopic ways than neat, arranged ones. A deck of cards, in perfect order from ace to king, in each suit has very low entropy. A thoroughly shuffled deck has high entropy. There are vastly more scrambled arrangements than perfectly ordered ones. The same is true for air spread evenly versus air compressed in one corner of a room, or for an egg versus the splatter when it breaks. The second law of thermodynamics states that in an isolated system, entropy tends not to decrease from one state to another. There is no absolute prohibition against a small decrease, but overwhelmingly, the likely evolution is towards states with more microstates available, because there are simply so many more ways for a system to be disordered than ordered. If you release gas from a small volume into a larger one, the vast majority of possible molecular paths will lead to it spreading out rather than spontaneously recompressing into the corner. This statistical tendency gives time a direction from low entropy to high, from more special to more typical. The movies, where shattered vases fly back together, are not forbidden. By the deepest equations, they are just unbelievably unlikely. Given the number of microstates involved, on Earth and in your daily life, the arrow of time is tied to many linked arrows. The psychological arrow, you remember past events but not future ones. The thermodynamic arrow, heat flows from hot objects to cold ones, not the other way around. The cosmological arrow, the universe expands from a denser, hotter state to a cooler, more diffuse one. All of these are connected to entropy, but underneath them lurks a quieter question. Why was entropy low? In the first place, why did the universe start off in such a special, highly ordered state that there is room for entropy to increase over billions of years? If the universe had begun in a generic configuration, if its matter and gravitational fields had started in a state with maximal disorder, there would be no thermodynamic arrow already at the beginning. There would be nowhere for entropy to grow, no room for stars to form, for gradients to drive processes, for complex chemistry, for life. Instead, we find ourselves in a cosmos where the early state was extraordinarily smooth on large scales. The cosmic microwave background, the radiation left over from early times, is almost uniform in temperature across the sky, with only tiny variations at the level of 1 part in 100,000. This smoothness is actually a low entropy condition when gravity is present, because gravity loves clumpiness. Here is the subtlety. If you ignore gravity, a smooth gas spread evenly is high entropy, because the molecules can be arranged in many ways while preserving uniformity. But once gravity is included, clumped states have higher entropy over long times. Matter, attracted by gravity, tends to gather into stars, galaxies, clusters. Eventually, for very large systems, black holes, which are believed to be the highest entropy objects of a given mass and size, a smooth universe with matter spread evenly is therefore a very special arrangement seen through the lens of gravitational entropy. It is not generic at all. From that smoothness, gravity can generate structure over time. Small initial fluctuations grow under their own pull. Gas collapses into halos, stars ignite, galaxies spin, black holes form, entropy rises. As the universe moves from smooth to clumpy, from simplicity to structured complexity, with enormous hidden disorder in the microscopic details of all those configurations. So the real mystery behind the arrow of time is not why entropy increases now, given a low entropy past. That part is well understood. Statistically, the puzzle is why the early universe had such low entropy, why its gravitational degrees of freedom were arranged in such a deceptively simple way, with space almost uniform and curvature nearly the same everywhere, on large scales. This is sometimes called the problem of the special beginning. It is not solved by saying things were very hot and dense. A hot, dense chaos could have been high entropy. Instead, the early state was hot and dense, but also extremely smooth in its large-scale structure. That smoothness is exactly what allows an arrow of time to exist at all. Cosmologists have proposed different kinds of explanations for this special beginning. One possibility is that it is simply a boundary condition, a given that must be accepted as part of the description of our universe. In this view, the equations of physics tell you how states evolve, but they do not themselves determine the initial state. You must specify that state separately by hand. Perhaps the universe just happens to have begun in a low entropy configuration with a nearly uniform distribution of matter and curvature. No deeper reason within current theories is known for that fact. If this is true, then the arrow of time is ultimately rooted in a brute fact about the initial condition, a fact that might not admit further explanation from within the same framework. Another class of ideas invokes inflation, the rapid accelerated expansion believed to have occurred at very early times. Inflation was originally proposed to explain why the universe looks so uniform over vast distances and why its geometry appears so close to spatial flatness. In inflationary models, a region of space filled with a particular field with high potential energy expands exponentially, stretching any initial irregularities to near uniformity. Quantum fluctuations during this phase are amplified to become the seeds of later structure. Inflation can therefore explain how a small patch with certain properties gets stretched to become the entire observable universe, and why that universe is so smooth on large scales. But when viewed through the lens of entropy, the story is more delicate. Inflation itself requires a low entropy initial patch. The inflating region must have certain conditions in order to begin the process at all. One can argue that once inflation starts, it can produce enormous volumes with conditions like ours, so that such regions are not rare within an inflating multiverse. Yet the question of why inflation began with the right field configuration and why in a low entropy state is not obviously resolved. Rather, the explanatory burden is shifted from the standard Big Bang to the inflationary phase. There is ongoing debate about whether inflation truly explains the arrow of time, or whether it assumes what it aims to explain in a different guise. A different approach appeals to deep laws that might constrain the allowed initial conditions. Perhaps not every imaginable state is physically realizable. Maybe only those states that obey certain consistency conditions can exist. For example, quantum gravity might restrict the geometry and topology of allowed spacetimes. Certain pathologies, such as closed time-like curves, could be excluded by deeper principles. In some proposals, there is a unique or highly preferred initial state selected by the structure of the underlying theory. If so, the low entropy of the early universe might not be an arbitrary choice, but a consequence of those deeper constraints. Work in quantum cosmology, holography, and other areas sometimes aims at such selection principles, seeking rules that pick out a simple, smooth initial condition as the natural starting point for a universe like ours. These ideas are intriguing but not yet definitive. We do not yet have an agreed-upon theory that uniquely fixes the beginning and demonstrably reproduces all observed properties of our cosmos. Cyclic scenarios offer yet another angle. If the universe does not have a single beginning, but instead undergoes repeated cycles of contraction, bounce, and expansion, the arrow of time might be linked to how entropy behaves across cycles. In some models, entropy increases from cycle to cycle, with each new expansion being larger or longer than the previous one. In others, certain mechanisms dilute or reset entropy during contraction or between cycles. Perhaps black holes evaporate or horizons change in ways that alter the counting of microstates. The details are complex and sensitive to the assumed dynamics. The key challenge is to avoid an accumulation of entropy that would eventually spoil the regularity of cycles, while still respecting the second law within each cycle. If a successful mechanism exists, cyclic cosmology could provide a different context for understanding the specialness of the beginning. What looks like a low entropy start to one cycle might be the result of processes that unfolded in a previous era, though even then, one can still ask why the overall system has the properties that allow cycles at all, and whether the chain extends infinitely into the past or has its own boundary in some deeper sense. While these debates continue among specialists, there is another thread, more personal, that runs through the arrow of time. Your own experience of being a self located in a flow from past to future is intimately tied to entropy. Memories are physical records written into matter, patterns in your brain, in your nervous system, in the traces you leave around you. For such records to exist, there must be processes that can create stable, low-entropy imprints from higher energy gradients. Your brain consumes energy to maintain structure, to store correlations between neural states and events in the world. Those correlations are what we call memories. They allow you to say, "I remember yesterday, but not tomorrow." There is no fundamental law in the microscopic equations that forbids records pointing the other way. A system could, in principle, contain correlations with what we label future events, but in a universe with a low-entropy past, the overwhelming tendency is for records to be laid down from earlier to later times. As entropy increases, your sense of a moving now and of a fixed past is shaped by that directionality. If the early universe had not been special, if entropy had been high from both temporal ends, the structure of records and memories might have been very different. Some speculative models imagine symmetric arrows pointing away from a central low-entropy state. Observers on each side would remember only their own lower entropy direction, experiencing time as flowing outward from the middle. But in our observed universe, we see only one arrow, from past smoothness to future complexity, from simple initial conditions to rich structures, including conscious beings who can contemplate the arrow itself. Philosophically, these considerations invite a reframing of the question, what came before time, instead of picturing a clock extending backward indefinitely. We might think, in terms of entropic structure, perhaps time as we experience it only makes sense in a regime where entropy gradients exist, where records can be created, where coarse-grained descriptions evolve. In typical ways, it might be that beyond a certain boundary in the history of the universe, the concept of a directed time parameter ceases to be useful. The laws may still have parameters, labeling configurations, but those parameters do not correspond to anything like the thermodynamic arrow we know. In that sense, asking what came before our arrow of time might be like asking what lies beyond the edge of a map, drawn only for a certain region. You can extend the paper, but unless the terrain follows the same rules, the familiar symbols no longer apply. For the purposes of falling asleep, you do not need to choose between these possibilities. You do not need to decide whether the low-entropy beginning is a brute boundary condition, a consequence of inflation, a selection by deep law, a feature of cycles, or an aspect of some as yet unknown theory. It is enough to appreciate that the arrow of time, which feels so immediate in your everyday life, is intimately linked to the structure of the universe, on its largest scales, to the smoothness of the early cosmos, to the way gravity builds structure, to the way entropy unfolds over billions of years. The fact that you remember yesterday but not tomorrow is connected to the fact that the microwave sky is almost uniform and that black holes carry enormous entropy. The cup cooling on your bedside table, the fading warmth of your body as you relax into rest are tiny expressions of the same tendency that shapes galaxies and stars and the long evolution from a simple beginning to a rich present. When you exhale and let your thoughts drift, you are participating in the arrow of time, letting entropy increase in small ways while your mind wanders through memories of the ordered past and expectations of a less determined future. All of it traces back to that special start, that low entropy state near what we call the beginning of time. Why it was so remains one of the deepest mysteries in cosmology, but its consequences include you, lying here now thinking about it on the gentle edge between wakefulness and sleep. There is a kind of quiet honesty at the heart of the scientific way of looking at the world. It does not promise certainty, it does not promise final answers. Instead, it offers something more modest and in its own way more profound, a method for asking careful questions, for checking ideas against reality, for refining what we think we know, step by step, measurement by measurement, across generations. When we turn this method toward the deepest questions about the origin of the universe and about what came before the beginning of time, we encounter both its greatest strengths and its natural limits side by side. To rest with that, to understand where science is powerful and where it must fall silent, is part of the calm of looking into the cosmic dark without demanding that it immediately speak. One of the central principles of modern science is testability. An idea is scientific to the extent that it makes contact with observation, that it leads to predictions or at least to constraints that can be compared with data. Sometimes the test is very direct. You predict a particle, you build a detector, you look to see if it appears. Sometimes it is more indirect. You work out how a theory that changes the cosmic expansion rate or the pattern of fluctuations in the early universe and then compare those patterns to the radiation. We can still measure, today in all cases, the link between theory and experiment is what keeps speculation anchored, prevents imagination from drifting, completely free of reality. In cosmology, our most important sources of such contact come from the sky itself, the cosmic microwave background, the relic glow, from a time when the universe was dense, hot, and filled with a nearly uniform plasma, carries subtle variations in temperature and polarization across the sky. Those variations record information about the conditions of the early cosmos, about the composition of matter and radiation, about the geometry of space. They even carry clues about the processes that seeded galaxies and clusters. Long afterward, when we test different models of the beginning, we often ask what pattern of fluctuations would this model produce? What spectrum of hot and cold spots? What correlations between different angular scales? Then we hold those predictions against the actual map of the microwave background, looking for agreement or contradiction. If a proposed scenario generates patterns that are clearly inconsistent with what we observe, it is ruled out or at least severely constrained. If it matches many features within current uncertainties, it remains viable but not uniquely favored, because other models may also fit the same data in slightly different ways. Beyond the microwave sky, we also use large-scale structure, the distribution of galaxies and clusters and voids across billions of light years. Subtle statistical measures of how matter is clustered on different scales carry information about the initial fluctuations, about how gravity and expansion have shaped them. Over time, we can probe the expansion history by observing distant supernovae, by measuring baryon acoustic oscillations, a kind of fossil imprint of primordial sound waves in the clustering of galaxies. We can study weak gravitational lensing, tiny distortions in the shapes of background galaxies caused by intervening mass. Together, these observations constrain how much dark matter exists, how strong dark energy is, how curvature behaves, whether the universe is spatially flat, open, or closed, and what kinds of scenarios for the early universe are compatible with what we see. On an even more ambitious front, physicists look for primordial gravitational waves, ripples in space-time generated by processes in the very early universe. These waves would leave a characteristic signature in the polarization pattern of the cosmic microwave background, a faint curl-like component known as B-mode polarization. Detecting such a signal would tell us about the energy scale of the early processes, possibly about inflation or about alternative mechanisms that produce the seeds of structure. So far, experiments have not yet seen a clear primordial signal, but they have set upper limits, which already exclude some simple versions of early universe models. Future instruments on the ground and in space will push these limits further, either revealing such a signal or tightening the constraints on what the earliest moments could have been like. All of these cosmic observables act like windows, narrow but precious, into times and conditions we cannot reproduce on Earth. They allow us to evaluate competing ideas, to see which descriptions of the early universe remain compatible with the patterns written into radiation and structure and expansion that we have now measured with great care. Yet, for all this power, the windows do not open infinitely wide. They do not tell us everything about what might have come before. The domains we can observe. One limitation is simply practical. We can only see so far. The observable universe is finite in every direction. We look back to a horizon beyond which light has not had time to reach us. Since the hot early phase, anything that happens outside our cosmic horizon is not directly visible. No light, no gravitational waves, no particles from those regions can reach us without violating the basic speed limit of relativity. This does not mean there is nothing beyond the horizon, but it means that events there cannot influence what we observe here except through their contribution to broad properties, like the overall curvature or in some cases, through rare, subtle signatures, such as collisions between bubble-like regions. If they ever occurred, the burden of proof for such signatures is high because the data are sparse and the patterns are easily mimicked by more mundane effects. Another limitation is that very different theories can sometimes give rise to very similar predictions within the range. We can measure. A simple example is the way different models of inflation, different shapes of the inflaton potential, or different mechanisms to generate fluctuations can nonetheless produce nearly the same power spectrum of temperature variations in the microwave background, with only small differences in higher-order statistics or in details of polarization. This makes it difficult to single out one unique model as the truth. Even when we have precise data, we can often carve away large regions of theoretical possibility space, but what remains is not a single point. It is a family of surviving candidates, a landscape of models that all agree. With current observations within error bars, this is one reason why multiple theories coexist. In modern cosmology, we do not yet have enough distinct kinds of data to discriminate sharply between all of them. In addition, many proposals are not yet developed to the point where detailed predictions can be calculated. Some are sketches of possible underlying pictures, suggesting new ways to think about time or about quantum gravity, without a fully worked-out formalism. For connecting those ideas to observables until they reach that level of precision, they remain interesting possibilities, but not directly testable, in the strong sense required to elevate them to confirmed science. There are also scenarios which make genuine predictions, but only for regimes we cannot practically probe. For example, some models might differ significantly from others, only at energy scales far beyond those attainable in any conceivable particle collider, or only at epochs so close to the notional beginning that their signatures are smoothed out or erased by later dynamics. In principle, the differences are real. In practice, they may never be distinguishable by any measurement. A physical being inside the universe could actually perform in that sense. The theories are empirically underdetermined by construction. Recognizing these limitations leads naturally to intellectual humility. When we speak about ultimate origins, we know much more than we did a century ago. We have precise measurements of cosmic expansion, of the ages of stars and galaxies, of the composition of dark matter and dark energy, of the patterns in the cosmic microwave background. We can trace the history of the universe from a fraction of a second after the hot early phase to the present day. With remarkable accuracy, we can say with confidence that the universe has been expanding and cooling, that light elements were forged early, that cosmic structure grew from small initial fluctuations. We can bound the properties of any scenario to describe earlier times. It must recover all of this as a limit. But when we try to leap beyond that first fraction of a second into the realm where quantum gravity dominates, where space-time itself may be fluctuating or emergent, we step into a domain where our theories are incomplete and where observations offer only faint, indirect guidance. It would not be honest to claim more than we can support with evidence or with consistent mathematics. Science, as a method, accepts this. It is built to live with uncertainty. Its strength is not that it gives final answers, but that it continuously tests, refines, and in some cases replaces its own conclusions in light of new data. It does not treat any current theory as sacred, only as provisional, the best we have so far open to revision. If nature sends us a clear signal to the contrary, this self-correcting nature is part of why scientific knowledge accumulates over time, even when individual models come and go, and even when certain questions remain unresolved for long periods. When we ask what came before time, we are pushing at the outer edge of what this method can currently address. We can frame the question in different languages, in terms of emergent time, in terms of wave functions, of universes, in terms of bouncing cycles or multiverse ensembles. We can examine which of these pictures are consistent with what we know from the microwave background, from large-scale structure, from the expansion history. We can map out what each picture would imply about possible new observables, such as primordial gravitational waves or subtle non-Gaussian patterns. In cosmic fluctuations, we can design experiments to search for those signatures. But we must also accept that it may turn out some of these ideas are forever beyond decisive test, or that the data will support several different frameworks equally well. Even in the best case, even if we someday find a mathematically elegant quantum theory of gravity that naturally produces a universe like ours, with a well-defined low-entropy beginning and an arrow of time, we may still be left with questions about why that theory and not another, why those laws rather than some alternative. Again, we encounter the boundary where how gives way to why, and where physics, as it is currently practiced, may simply say, beyond this point I do not know. There is a temptation, when faced with such boundaries, to fill them quickly with certainty of one kind or another, to declare that one picture must be true because it feels right, or because it is aesthetically pleasing, or because it resonates with a philosophical or spiritual intuition. Some of those resonances may be meaningful for individuals, but within science they cannot substitute for testable content. The discipline is careful about this distinction. It strives to separate what the data demand from what we hope or fear or find elegant. In our imaginations, that separation can feel austere, even a little cold, but it is also freeing. It allows wonder to coexist with uncertainty without forcing us to pretend we have answers we do not yet possess. From a more gentle angle, you can see this as a kind of invitation. You are not required to resolve every mystery before you rest. You do not have to decide which pre-Big Bang scenario is the right one, or whether time truly had a beginning, in a strict sense. You can let the different ideas sit side by side in your mind as possibilities, some more constrained than others, some more speculative, some still only sketches, awaiting clearer form. You can appreciate how much has already been learned, how carefully the cosmic story has been reconstructed from tiny signals in old light and faint patterns in distant galaxies, while also acknowledging that there is an open horizon of not knowing, beyond that, a horizon that may never close completely. It is also worth noticing that the persistence of the unknown does not reduce the value of what science has done. If anything, it highlights how extraordinary it is that finite beings on a small planet have managed to infer so much about events billions of years past, billions of light years away from a handful of measurable quantities: the temperature of a background glow, the brightness of exploding stars, the clustering of galaxies, the redshift of spectral lines. Out of these have emerged a coherent picture of cosmic history, with clear stages and transitions and constraints on what could have preceded them. That accomplishment stands, even if the questions at the very edge of time itself remain partially unanswered. In the quiet of your own thoughts, you might allow a different kind of wonder to arise, not only wonder at what we know about the cosmos, but wonder at the fact that there are limits, at all, that there are questions which resist complete domestication by equations and measurements, that there is room for open-ended curiosity that does not collapse into final statements. Perhaps this is not a deficiency, but a feature of a universe that sustains both comprehension and mystery, both pattern and open space, for further thought. As you lie here, breathing slowly, you can picture the instruments that watch the sky, radio dishes catching ancient photons, satellites mapping faint anisotropies, telescopes charting galaxies and supernova, laser interferometers listening for distant gravitational waves, humanity extending its senses outward to test ideas about beginnings and boundaries. You can also picture the blackboard covered in symbols, the lines of code simulating structure formation, the quiet rooms where people sit, trying to reconcile quantum mechanics with gravity. These are expressions of the same impulse to ask, to model, to check, to revise, to accept what the evidence allows and to admit what it does not yet reveal. Science can tell you a great deal about how time behaves within the universe, how it is intertwined with space, how it emerges in certain descriptions, how entropy gives it direction. It can show you that the phrase "the beginning of time" has a precise meaning. Within particular models, linked to the breakdown of classical descriptions, to the onset of quantum gravitational regimes, it can constrain what any story about before must look like. If it is to be consistent with the cosmic microwave background, with large-scale structure, with nucleosynthesis, with all the observational pillars of modern cosmology, It can even suggest new ways to think about before, as a region where time is emergent or where familiar notions of cause and effect must be reinterpreted. But there is a line beyond which science simply says, here, our models are incomplete, our data are silent. Beyond this, we do not know. And somehow, it can be deeply relaxing to accept that, to let go of the pressure to resolve every last detail, to allow some questions to remain open, at least for now. You are part of a species that has learned to read the faint afterglow of a hot beginning, to infer the presence of dark matter and dark energy, to map the growth of structure across cosmic time. You are also part of a universe that may keep its ultimate origin story partly veiled, not out of hostility, but simply because the tools we use have a natural domain within which they shine, and beyond which they fade into a softer kind of wondering. As your eyelids grow heavier, you can rest in that balance between knowledge and mystery, between what science can say clearly and what it cannot yet address. Let the unanswered questions be like distant galaxies, visible as tiny smudges on a deep sky image, real, present, but far enough away that you do not need to reach them tonight. You can simply lie here, under the same laws, the same patterns, the same cosmic history, letting your thoughts slowly drift on the quiet realization that it is all right not to know everything. That wonder does not require certainty, only attention and a willingness to look and to keep looking. Even knowing that some horizons may never be crossed, there is a moment when the questions stop pushing forward and simply rest alongside you, not solved, not silenced, just quieter, like distant stars, still shining but no longer demanding your attention. You are lying here, breathing slowly in a small room on a small world, orbiting an ordinary star in one arm of one galaxy out of hundreds of billions scattered across the observable universe. The scale of it all is almost impossible to hold in a single thought, and yet your mind has spent this time touching ideas that stretch from the first fractions of a second of cosmic history to questions about whether time itself has a beginning or an outside. You have allowed your awareness to follow those questions upward and outward beyond everyday concerns, beyond the surface of things, into a domain where the language of physics meets the boundary of the knowable. You have heard about an expanding universe where galaxies drift apart not because they are flying through some pre-existing emptiness, but because space itself is stretching. You have heard that what we call the beginning is not an explosion at a point, but a hot, dense, rapidly expanding state, filling all of space at once. You have followed the idea that time, as we measure it, is woven into that expansion. That cosmic time is defined within the history of the universe. Rather than sitting outside it as a separate background, you have glimpsed the strange boundary where our present theories begin to fail, where general relativity, describing smooth space-time, and quantum mechanics, describing discrete quanta of fields and matter, are both needed but not yet reconciled. You have heard of the Planck scale, tiny lengths and tiny times, so small that our familiar notions of space and duration likely break down. You have encountered the idea that singularities in equations are not physical points where infinity truly exists, but places where the equations stop making sense, signposts that say, here a deeper description is required. You have let your thoughts rest on the possibility that time itself may be emergent, not fundamental, that what you experience as the flow of moments could arise from statistical behavior, from entropy, from the arrangement of matter and energy. You have met the block universe picture where past, present, and future are all contained in a single four-dimensional geometry, and where the sense of now is tied to your own trajectory through space-time rather than picked out by the universe itself. You have entertained the quietly radical idea that asking what came before time may be like asking what lies north of the North Pole. A question whose grammar works while its content does not. You have brushed against quantum cosmology, where the whole universe is treated as a quantum object described by a wave function, not just particles, but space-time itself, in superposition. You have heard of proposals where the universe has no sharp beginning, where time, near the earliest stages, behaves more like a spatial direction, where the concept of a boundary in time is replaced by a smooth rounding off. In a deeper geometry, you have seen that in such pictures, the question of before is softened or dissolved, not through word games, but through a different structure of the laws themselves. You have drifted through bouncing universes that contract then re-expand through cyclic scenarios where cosmic history plays out in repeated aeons, where each vast era grows, aging galaxies, cooling radiation, increasing entropy, until at last new conditions allow a reset. You have visited models where brains, higher dimensional surfaces, collide, and the energy released looks to interior observers like a Big Bang. You have seen that these ideas are not myths in poetic clothing, but attempts to encode the mathematics of quantum gravity and higher dimensional theories into coherent cosmic histories, even if they are still incomplete. You have allowed your imagination to explore eternal inflation, where inflation is not a single brief episode, but an ongoing process in some regions of a larger space-time, where quantum fluctuations cause some patches to stop inflating and become bubble universes with their own local laws, while other regions continue to inflate without end. Your own observable universe in that picture is one bubble among many, a finite domain with a specific history nested inside a much larger and perhaps unending structure. You have recognized that such models raise difficult questions about testability, about probabilities, across infinite ensembles, about whether statements about other bubbles are physically meaningful or forever speculative. You have touched string-theoretic scenarios where the fundamental objects are not point-like particles but tiny vibrating strings, where extra dimensions beyond the familiar three of space are compact, curled up, too small to see directly, where dualities relate contracting phases to expanding ones, hinting that what looks like a beginning from one perspective can be reinterpreted as a transition from another. You have heard whispers of holography, the notion that the information content of a region might be encoded on a lower dimensional boundary, that the degrees of freedom of space-time could be fewer than naive counting suggests, that our universe may admit descriptions in which bulk geometry emerges from more abstract, microscopic structures. You have contemplated the word nothing and seen how slippery it becomes under scientific scrutiny. In physics, the vacuum is not empty. It is a state of minimum energy for quantum fields, still animated by fluctuations, still governed by laws. Even nothing in that sense assumes a framework, a set of rules within which fields and energies are defined. The question of why there is something, rather than nothing, shifts to why there are laws at all, why there is a structure in which a vacuum is even a meaningful concept. Science can trace systems back to vacuum-like states, can describe how fluctuations might give rise to universes, can show how those universes evolve, but the origin of the deeper framework remains a mystery outside its current reach. You have learned that the arrow of time is intimately connected to entropy, that the reason you remember the past and not the future, the reason broken cups do not spontaneously reassemble, is tied to the extraordinarily low entropy state of the early universe, the smoothness of the cosmic microwave background. The absence of large-scale gravitational clumping at early times is not trivial. It is a profound clue about the conditions at or near the beginning. Any story about ultimate origins must account for this specialness, why the universe started so ordered, when high entropy would be far more typical. Under naive counting, many of the deepest questions about before are as much about this as about any specific event before the hot phase. You have also noticed how carefully science distinguishes between levels of confidence, between ideas with strong observational support, those still being tested, and those that are more speculative, or not yet testable. You have seen that testability through contact with data is not a formality, but the very heart of the scientific approach. Without it, theories can proliferate without limit, no longer anchored to what the universe actually presents. When we look, you have heard how measurements of the cosmic microwave background, of large-scale structure of the expansion history, and perhaps someday of primordial gravitational waves, all act as constraints, filtering out models that do not fit, narrowing, but not entirely eliminating, the space of possibilities. And finally, you have rested with the idea that even with all this there are boundaries. Science can say much about how the universe behaves. After a certain early time, it can place meaningful limits on what any viable theory of earlier stages must look like. It can suggest plausible schemes for emergent time, for quantum beginnings, for cycles, for multiverses. It can test some aspects of those schemes against the sky, but it cannot yet, with honesty, declare one single story about what came before time as uniquely established. There remain gaps where our equations are incomplete, where our data are silent, where multiple frameworks fit the same observations, where deep questions about why there are laws or why there is something, rather than nothing, are simply not addressed by the tools we currently possess. And so here you are, at the end of this long arc of reflection, lying in the dark with your own breathing as a quiet metronome surrounded by the ordinary, familiar textures of your life, and also by the vast, largely invisible structure of a universe, 14 billion years or so into its expansion, filled with galaxies and clusters and dark matter and dark energy, underlain by quantum fields and space-time geometry, governed by laws we partially understand and partially do not. You are a small part of that totality, a pattern of matter and energy, temporarily organized into a self-aware system, able to ask what came before time, able to feel wonder and uncertainty at the same moment. There is no requirement that you resolve these questions tonight, no exam, no demand for a final answer. You are allowed to let the ideas that you have heard gently loosen like sand flowing through open fingers. You can let the technical distinctions between models fade a little, leaving behind a softer impression that the universe is both intelligible and mysterious, that we have maps for large regions but not for every edge, that not knowing is not a failure but a natural state for finite minds in a large reality. If you shift your attention inward, you can notice how your sense of time right now is already changing. Moments blur, thoughts elongate or fragment as sleep approaches. The precise sequence of ideas starts to matter less. Then the overall feeling of spaciousness of being held within a story that does not need to be finished. For you to rest, your brain will continue its own activity in dreams, in memory consolidation, in quiet housekeeping, but your conscious awareness will soften, letting go of its tight grip on before and after, on questions and answers, on cosmology, and on yourself. Somewhere, far above you, if the sky were clear, photons from the cosmic microwave background would be streaming past, relics from an early time still flying across the universe, carrying information about that hot, dense phase in which everything familiar was once compressed. Those photons do not know. They are ancient. They do not know. They have been used to test models of inflation or quantum cosmology. They simply follow geodesics in space-time, curved by matter. And energy, they are part of the fabric through which you also move on a very different scale. Your own life is another pattern in the same universe, brief from the cosmic point of view, but dense with its own structure, its own relationships, its own questions. The fact that you can lie here and let your mind range across the beginning of time, the possibility of before, the nature of nothingness, and the limits of scientific knowledge is itself a quiet marvel. Out of the cooling plasma of the early universe, out of collapsing gas clouds that formed stars and planets, out of chemistry and evolution has come a being who can generate abstract models of the entire cosmos, who can detect ancient radiation with instruments, who can write equations that describe gravity and quantum fields, who can accept both what is known and what is not, and who can, at the end of a day, let those thoughts lull them towards sleep. If any single conclusion is offered, it is not a specific answer to what came before time. It is something gentler, that it is all right to live inside an unfinished story, to inhabit a universe where some chapters are well mapped and others remain blank, to be curious without being restless, to find calm, not only in clarity but also in mystery. You can carry that attitude like a quiet instrument tuned to both evidence and wonder into your waking life. And you can set it down for now as your eyes grow heavy and your thoughts begin to loosen into dreams somewhere. The cosmos continues its expansion, galaxies drift, stars are born and die. Planets orbit, dark matter halos quietly shape structure, quantum fluctuations play out at unimaginably small scales. Time, in the physical sense, flows according to the dynamics of space-time. Entropy increases, the arrow of time continues its one-way direction from low entropy past to higher entropy future. All of that will go on while you sleep. You do not need to attend to it. the universe can manage without being watched. For this moment, all that matters is the small region of space-time you currently occupy, the air in your lungs, the gentle rhythm of your breathing, the contact with whatever supports you, the way your body grows heavier as muscles release and thoughts grow slower, less sharp, more diffuse. Let the question of what came before time recede to the far background of your awareness, like a distant galaxy, still there, still real, but no longer at the center of your attention. In the foreground, there is only your breath, your weight, the darkness, and the knowledge that it is enough for tonight to rest inside a universe that is vast, law-governed, partially understood, and still beautifully, mysteriously unfinished. As you drift, you can let one last thought pass through softly without needing to hold it, that you are for a brief time a conscious part of the same cosmos you have been contemplating, and that whether or not we ever fully answer what came before, the act of asking already connects you to something larger than your own life. That connection can be quietly comforting, like a hand lightly resting on your shoulder, guiding you not towards solutions, but towards sleep. You can let go now, let the questions dim, let the universe continue on its vast trajectory while you gently fall asleep.